Look up at the night sky on a clear, dark evening. You see a breathtaking tapestry of stars, distant galaxies, and the silent, majestic sweep of the cosmos. It's beautiful and it feels vast. But here's a question that has haunted philosophers and scientists for centuries. Is that magnificent view, that seemingly infinite expanse, all there is? What if the universe we perceive with our eyes and our most powerful telescopes is only a fraction of the true reality? What if the cosmos is hiding profound, almost unbelievable secrets just beyond the edge of our perception? This is not just a flight of fancy, it's a frontier of modern science, a realm where physics and philosophy collide in the most spectacular ways. We are about to embark on a mind-bending journey together, a deep dive into 30 of the most incredible theories that challenge everything we think we know about existence itself. From the possibility of hidden dimensions curled up smaller than an atom to the radical idea of a cosmic consciousness that connects all things, we will explore concepts that stretch the very fabric of reality. This is a conversation about the universe's greatest mysteries, the puzzles written into the laws of physics that suggest our world is far stranger and more wonderful than we ever imagined. The tone here is one of shared discovery. We're not delivering a dry lecture, we're unraveling secrets side by side. We'll unpack ideas that might sound like science fiction but are grounded in serious scientific inquiry. And by the end of our time together, you might just find yourself looking at the world and the sky above in a completely new light. So get comfortable, open your mind, and prepare to question everything. The journey into the universe's hidden realities starts right now. And so we arrive at our very first theory, a concept so profound it challenges our most basic understanding of space itself. It's called the holographic principle, and it proposes a truly staggering idea. Our universe, with all its rich, three-dimensional depth, the spiraling galaxies, the towering mountains, the very space you and I occupy might be nothing more than a magnificent projection. A cosmic illusion. According to this theory, all the information needed to create this vast, 3D reality is actually encoded on a distant, two-dimensional surface that surrounds us, like the shimmering data on the surface of a DVD encoding an entire movie. Think about a standard security hologram on a credit card. That flat, shiny strip contains all the information necessary to generate a stunningly detailed three-dimensional image that you can look around. The holographic principle suggests our entire universe operates on a similar, albeit infinitely more complex, principle. We are, in a sense, living inside the hologram. This revolutionary idea didn't emerge from pure philosophical speculation. It was born from one of the most perplexing puzzles in modern physics, the black hole information paradox. When something falls into a black hole, according to Einstein's general relativity, it's gone forever, lost behind the event horizon. But quantum mechanics has a fundamental rule: information cannot be destroyed. So, what happens to all the information about an object that gets sucked in? Does the universe just forget it ever existed? Physicists like Leonard Susskind and Gerard T. Hooft wrestled with this problem for decades. Their groundbreaking work revealed something astonishing. They found that all the information about everything that falls into a black hole doesn't vanish. It gets perfectly encoded and stored on the black hole's event horizon, its two-dimensional boundary. The three-dimensional interior, the black hole itself, is entirely described by the information painted on its 2D surface. This discovery was the seed. If this is true for a black hole, could it be true for the entire cosmos? Could our observable universe, with its own cosmological horizon, also be a holographic projection from a flat, informational surface at the very edge of everything we can see? The implications of this are almost too vast to comprehend. It would mean that the world we experience as solid and voluminous is, at its most fundamental level, a kind of optical trick played on us by the underlying laws of physics. The richness of our 3D reality is an emergent property, a translation of data from a lower dimensional reality. It suggests a profound interconnectedness where every event here in our world is intimately linked to processes happening on that distant theoretical boundary. While this remains a highly theoretical framework, it represents a monumental shift in how we approach the nature of reality, blurring the line between the solid world we inhabit and the informational code that might ultimately define it. Building directly on the idea that our reality might be a grand projection, we encounter a theory that expands the stage of existence itself to an almost unimaginable degree. If the holographic principle makes us question the substance of our universe, the concept of the level 1 multiverse questions its uniqueness. This idea springs from a fairly straightforward, yet utterly staggering, logical consequence of our best models of the cosmos. We know the universe is expanding, and the leading theory for its initial moments, called cosmic inflation, suggests that this expansion happened at an unimaginable rate in the first fleeting fraction of a second. This process likely smoothed out the universe, making it relatively uniform on the largest scales. And if space is truly infinite, or at least so vast it might as well be, then something incredible must be true. In an infinite, fairly uniform cosmos, the arrangement of particles cannot be unique forever. There are only a finite number of ways particles can arrange themselves within any given region, even a region as large as our entire observable universe. So, if you have an infinite expanse to work with, those finite arrangements must repeat. They have to. You simply run out of new patterns. This leads to a conclusion that is both awe-inspiring and deeply personal. Somewhere in a galaxy impossibly far beyond the reach of our most powerful telescopes, there is another planet exactly like Earth, not just similar but a perfect replica, where every atom is in the same place as it is here right now. On that planet there is another you, and in that moment they are reading these very same words, or perhaps a different version of them, or maybe they've chosen to do something else entirely. Because the repetitions don't stop with one copy. If space is infinite, then there are not just two of these Earths, but an infinite number of them. Every possible variation that the laws of physics allow is played out somewhere. There's a version of you who became an astronaut, a version who made a different choice at a key moment in their life, and versions where history itself unfolded differently. Every life that could be lived is being lived across the boundless cosmic tapestry. This isn't science fiction. It's a direct, if mind-boggling, interpretation of our current understanding of cosmology and the implications of infinity. We are not talking about branching timelines or parallel dimensions in the quantum sense. This level 1 multiverse exists within the same continuous space and time that we do. It's just so overwhelmingly vast that these identical regions are forever separated from us by distances so great that light from them will simply never, ever reach us. They are beyond our cosmic horizon, islands in an endless sea. This idea forces us to confront our place in the cosmos not just as inhabitants of a single world, but as one single iteration of a pattern that repeats without end. It redefines the meaning of possibility, suggesting that what we consider our unique lives and choices are, on a cosmic scale, just one variation in an infinite ensemble of reality. But while the level 1 multiverse suggests copies of our own universe are out there, the level 2 multiverse presents something even more radical. Not just copies of our reality, but entirely different realities born from different rules. This idea stems from a deeper look at the theory of cosmic inflation, the incredibly fast expansion of the early universe. Some versions of this theory propose that this inflationary process isn't a one-time event that started and stopped. Instead, it might be eternal. Picture a vast, simmering ocean of what physicists call a false vacuum, a high-energy state of space itself that is constantly and furiously expanding. This expansion is so rapid that it stretches space faster than light, but this ocean isn't perfectly uniform. Like a pot of water coming to a boil, tiny bubbles spontaneously form within this inflating sea. Each of these bubbles is a region where the inflationary energy suddenly drops, and the frantic expansion within that localized area slows to the more sedate pace we see in our universe today. Each of these bubbles becomes its own separate, self-contained universe, forever causally disconnected from our own and from all the others. These aren't just different regions of space, they are fundamentally different realities. When each bubble universe nucleates, it essentially rolls the cosmic dice on the fundamental laws of physics. The physical constants that define our reality, the strength of gravity, the mass of an electron, the number of spatial dimensions, are all frozen into place within that bubble. In one bubble universe, gravity might be so strong that stars form and burn out in mere millennia. In another, the electromagnetic force could be too weak to allow atoms to bond, preventing chemistry and life as we know it from ever arising. Our universe appears finely tuned for life. If gravity were slightly stronger or the cosmological constant a little different, stars and planets might never have formed. The bubble universe theory provides a powerful answer to this fine-tuning problem. It suggests that in an endless, frothing sea of budding universes, a vast majority are sterile, empty, or collapse instantly. But statistically, in a landscape of infinite possibilities, a few bubbles by pure chance will have just the right combination of constants to allow for galaxies, stars, planets, and life. We don't live in a special universe, we simply live in one of the rare, habitable bubbles. We are the product of a cosmic lottery we didn't even know we had entered. Imagine for a moment the grandest possible landscape, a cosmic foam where every bubble is an entire cosmos, each with its own unique physics, its own history, and its own potential for wonders we can scarcely imagine. Some bubbles might contain forms of matter and energy that don't exist in our own, leading to phenomena that would seem like magic to us. Others might have 5 fundamental forces instead of our 4, or exist in 7 spatial dimensions. This vision transforms our perspective from inhabitants of a single universe to residents of one tiny apartment in an infinite skyscraper of realities, a structure so vast that its full scope is forever beyond our reach. But if the bubble universes of level 2 feel distant and alien, the third level of the multiverse brings the infinite much, much closer to home. It suggests that a new universe is not just born in some distant inflating space, but is splitting into existence right here, right now, with every single quantum event. This is the many worlds interpretation of quantum mechanics, and it proposes that our reality is perpetually forking into an unimaginable number of parallel timelines. To understand this, we need to revisit one of the most famous thought experiments in all of science, Schrödinger's cat. In the classic version, a cat is placed in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers a mechanism that breaks the vial, killing the cat. Quantum mechanics tells us that until we open the box and look, the atom exists in a superposition. It is both decayed and not decayed at the same time. This logically implies the cat is both alive and dead, a bizarre state that only resolves into one definite outcome when we observe it. This moment of resolution is called the collapse of the wave function, and for decades it has been a central yet deeply puzzling part of quantum theory. Why does observation cause this collapse? What counts as an observer? The many worlds interpretation proposed by Hugh Everett in the 1950s offers a breathtakingly elegant, if startling, solution. The wave function never collapses. According to Everett, when the radioactive atom interacts with the Geiger counter, the entire system becomes entangled, but instead of collapsing into one state, the universe literally splits into 2 separate, equally real branches. In one branch, the atom decayed, the mechanism was triggered, and the cat is dead. In the other branch, the atom did not decay, and the cat remains alive and well. Both outcomes happen, There is no single mysterious moment of collapse because both possibilities are fully realized, each in its own newly created universe. The act of opening the box doesn't cause a single reality to be chosen. It simply reveals which branch of reality you are in. The you in one universe sees a dead cat and is saddened. The you in the other universe sees a live cat and is relieved. Both versions of you are equally real, but from that moment forward, they are forever separate, unable to communicate or interact. This interpretation completely reframes our understanding of reality. It removes the special role of the observer and presents a picture of the cosmos that is, at its heart, perfectly deterministic. The universe isn't random. It simply explores every single physical possibility available to it. Every time a photon hits a mirror and could be reflected or absorbed, the universe splits. Every time an electron can take one of two paths, the universe splits. And on a human scale, every time you face a choice what to have for breakfast, which job to take, whether to turn left or right, the universe branches to accommodate every possible decision. There isn't a single timeline of history. There is a continuously branching tree of every possible history that could ever unfold. There's a universe where you took that other job, a universe where a different candidate won the last election, and a universe where the dinosaurs never went extinct. This isn't about traveling to the past and changing things. It's about the fact that every possible outcome is realized in its own world, and we simply experience one thread of this vast, ever-expanding tapestry of existence. The sheer scale is beyond human comprehension. The number of these parallel worlds is not just vast, it is infinite, burgeoning with every passing nanosecond as countless quantum events cause the fabric of reality to perpetually divide and multiply. Now, if the many worlds interpretation suggests that every possible quantum outcome blossoms into its own reality, then the fourth and final level of the multiverse takes this idea to its ultimate, most abstract conclusion. This is the mathematical universe hypothesis proposed by physicist Max Tegmark, and it presents perhaps the most radical vision of all. It argues that our physical reality isn't just described by mathematics, a useful tool we invented, but that our universe in its entirety is a mathematical structure. Think about that for a moment. The chair you're sitting on, the stars in the sky, the very consciousness you're using to process these words are not just things that can be modeled with math. They are, at their most fundamental level, a complex, self-aware mathematical pattern. According to this hypothesis, the universe doesn't simply obey mathematical laws, it is those laws. The physicality we experience is an emergent property of an underlying, abstract mathematical truth. This leads to an even more staggering implication. If our universe is one specific mathematical structure, then what about all the other possible mathematical structures? Mathematics is a vast landscape of logically consistent systems, from the simple geometry of a triangle to the convoluted intricacies of hyperdimensional algebras. The mathematical universe hypothesis states that every single one of these consistent structures exists as a physical reality. A universe governed by the rules of basic arithmetic is out there. A cosmos where Euclidean geometry in 5 dimensions defines the laws of physics is equally real. There are worlds where the number pi has a different value, where the concept of prime numbers doesn't exist, or where the very logic we rely on, like the law of non-contradiction, simply does not apply. In this Level 4 multiverse, the Level 1, 2, and 3 multiverses are merely small subsets, specific mathematical structures that happen to contain internal descriptions of branching timelines and inflating bubbles. This is the multiverse of all possible multiverses. Consider the profound consequences for the fine-tuning of our own cosmos. We often marvel that the constants of nature seem perfectly calibrated for life. But if the mathematical universe hypothesis is correct, this isn't a mystery to be solved, it's a selection effect. We could not possibly find ourselves conscious in a mathematical structure that doesn't support complex computation and self-aware substructures which we call life. We don't inhabit a special universe, we simply inhabit one of the mathematical structures complex enough to allow for beings who can contemplate their own existence. This idea completely redefines the nature of existence itself, suggesting that the Platonic realm of perfect mathematical forms, which philosophers have debated for millennia, isn't a separate, idealized world. It is the world, it is all the worlds, every equation ever written, every geometric proof ever conceived, is not an abstract description of a reality, but a direct glimpse into a reality that physically exists somewhere in the ultimate ensemble of all that is possible. Shifting our gaze from the abstract landscapes of mathematical realities, we arrive at a theory that seeks to weave the fabric of the cosmos from the smallest possible threads. This is string theory, a framework so ambitious it aims to be the ultimate theory of everything, uniting the colossal realm of gravity with the spooky quantum world of the very small. For decades, these two pillars of physics, Einstein's general relativity and quantum mechanics, have been famously at odds. General relativity paints a beautiful, continuous picture of space and time as a smooth, curving fabric, perfectly describing the dance of planets and galaxies. Quantum mechanics, on the other hand, reveals a chaotic, probabilistic subatomic world where energy comes in chunks and particles pop in and out of existence. The two theories work flawlessly in their own domains, but when forced to meet, like at the center of a black hole or the moment of the Big Bang, the mathematics breaks down into nonsensical infinities. Physicists have long dreamed of a single, elegant theory that can harmonize these two discordant views of reality. String theory is a leading and profoundly captivating candidate for that grand unification. So, what is the fundamental insight of string theory? It begins with a radical reimagining of what everything is made of. For the past century, the standard model of particle physics has described the universe's building blocks as point-like, zero-dimensional particles, electrons, quarks, and so on, with no internal structure. Think of them as infinitesimal dots. String theory proposes that at the very smallest scales, at the so-called Planck length, these are not dots at all. Instead, the most fundamental entities are unimaginably tiny, vibrating loops or snippets of energy strings. And just like a single violin string can vibrate at different frequencies to produce every note in a symphony, a single fundamental string can vibrate in different modes to produce every different kind of particle we observe. One specific resonant pattern might manifest as an electron, another distinct vibration might create a quark, and yet another different pattern could give rise to the photon, the particle of light. In this breathtaking vision, the entire cosmic zoo of particles is reduced to a single type of object, simply humming different tunes. The universe at its heart is a kind of music. This elegant idea, however, comes with an extraordinary requirement, one that catapults us straight back into the realm of hidden realities. For the math of these vibrating strings to work consistently, to produce a universe with gravity and the forces we know, they cannot simply vibrate in the three spatial dimensions we're familiar with: length, width, and height. The equations of string theory only make sense in a universe with more dimensions. Most versions require a total of 10 or even 11 spatial dimensions. This immediately raises a pressing question. If there are all these extra dimensions, where are they? Why don't we see them, move through them, or experience them? The leading explanation is a process called compactification. Imagine a long, thin garden hose. From a great distance, it looks like a simple one-dimensional line. But if you get very close, you discover it has a second dimension, a circular cross-section curled up into a tiny, tiny circle. The theory suggests that at every single point in our familiar three-dimensional space, there are 6 or 7 additional spatial dimensions, but they are curled up and compactified on a scale so infinitesimally small a billionth of a trillionth of the size of an atomic nucleus, that they are completely hidden from our perception and our most powerful particle colliders. The specific, intricate shapes into which these extra dimensions are curled are known as Calabi-Yau manifolds. These are not simple circles or spheres. They are complex, multi-dimensional geometric shapes with a stunning array of holes and twists. The topology of a particular Calabi-Yau shape, the number of holes it has, and how it's folded determines the way strings can vibrate within it. And since the vibration of a string dictates the properties of the particle it becomes, the specific geometry of these hidden dimensions ultimately dictates the laws of physics in our visible universe. The mass of an electron, the strength of the nuclear forces, even the number of generations of particles, all of these fundamental features could be a direct consequence of which particular Calabi-Yau manifold our cosmos is built upon. This means that the reason our universe has the specific physical laws it does might be a direct result of a cosmic lottery that selected one specific geometry for these extra dimensions out of a staggering landscape of perhaps 10 to the 500 possible shapes. This is the immense promise and the profound challenge of string theory. It offers a truly beautiful and unified vision of reality, where all forces and all matter emerge from the harmonious vibrations of one fundamental object. It provides a natural place for gravity with the graviton, the hypothetical particle mediating the gravitational force, emerging as just another vibrational mode of a string. Yet, for all its mathematical elegance and explanatory power, string theory currently exists in a realm of speculation. The energy levels required to directly probe these strings or to detect the effects of these extra dimensions are far, far beyond what any particle accelerator we can build will ever achieve. It makes predictions, but we currently lack the technological means to test them. For some, this lack of experimental verification is a critical flaw. For others, the sheer mathematical consistency and beauty of the theory are compelling reasons to continue the search for indirect evidence. It stands as a monumental testament to human curiosity, a daring attempt to read the hidden score of the universe, a composition written not in particles, but in the resonant vibrations of strings echoing through a space of many more dimensions than we can see. Just when the idea of tiny, vibrating strings in 10 dimensions seems to capture the full strangeness of fundamental physics, the plot thickens. You see, as physicists delved deeper into string theory, they encountered an unexpected puzzle. Instead of one single, elegant theory, they found 5 different versions, each with its own mathematical structure and type of strings. It was as if they had 5 different maps of the same unknown continent, all seemingly correct but not quite matching up. This was deeply unsatisfying for a quest aiming for a single, ultimate theory of everything. The solution to this conundrum emerged in the 1990s with a revolutionary leap known as M-theory. Think of M-theory as the master theory, a grand, overarching framework that reveals the 5 string theories not as rivals, but as different facets of the same, deeper truth. They are like different shadows cast by a single, more complex object when viewed from different angles. M-theory doesn't just unify the forces of nature. It first unified the theories that were trying to describe them, and in doing so, it introduced concepts that are even more mind-bending than strings. One of the most profound revelations from M-theory is the existence of objects called brains, which is short for membranes. We're familiar with a point which has 0 dimensions, a string, which is a 1-dimensional line, and a membrane, which is a 2-dimensional sheet. M-theory proposes that these objects can exist in many more dimensions. A 2-brain is a 2-dimensional membrane. A 3-brain has 3 spatial dimensions, and so on, all the way up to higher dimensional structures. And here is the truly staggering part. One particular type of brain, a 3-brain, could be nothing less than our entire observable universe. In this brain world scenario, everything we know, every galaxy, every person, every atom, is confined to the 3 spatial dimensions of this immense floating membrane. We are not just in a three-dimensional space, we are on a three-dimensional object. This leads to a completely new picture of the cosmos. Our universe, this three-brain, is not floating in empty, three-dimensional space. It exists within a much larger, higher-dimensional arena known as the bulk. The bulk could have 10 or 11 spatial dimensions, and our brain is simply one object drifting within it. Why can't we perceive or move into these extra dimensions of the bulk? The forces that hold our world together, the electromagnetic force and the nuclear forces, are like glue that binds particles to the surface of our brain. These forces are so powerful that they trap everything we're made of, all matter and energy, firmly onto our three-dimensional home. We are like ink trapped on the surface of a page, unable to lift off into the volume of the book. But there is one fundamental force that is different: gravity. Gravity, according to this model, is not confined to our brain. It can leak out, spreading its influence into the higher dimensional bulk. This could provide a natural explanation for why gravity is so phenomenally weaker than the other forces. Its strength is not concentrated on our brain but is diluted as it spreads out across the extra dimensions. We are only feeling a faint shadow of gravity's true strength. Now, take this vision of a universe as a vast, floating membrane and consider the most dramatic event in cosmic history, the Big Bang. What could have caused a singularity of infinite density and temperature to suddenly flare into existence, spawning the entire cosmos? The brain world scenario offers a spectacular possibility. What if the Big Bang wasn't a singularity in space and time, but the aftermath of a colossal collision? Imagine two of these immense brains, each a full universe, drifting through the bulk. Over eons, they could slowly move toward one another, and then, in a cataclysmic instant, they smash into each other. The energy released in such a collision would be beyond comprehension, enough to flood a brain with an immense fireball of matter and radiation, instantly heating it to trillions of degrees and igniting a period of rapid expansion. From our perspective, trapped on one of those brains, this event would look exactly like the beginning of time, a hot, dense Big Bang. In this model, the universe isn't born from a single point of nothingness, but is reborn from a cyclical encounter between cosmic membranes in a higher dimensional space. This opens up the possibility that the Big Bang was not a one-time creation event, but one chapter in an endless cycle of collisions, expansions, and quiet drifting, a cosmic heartbeat echoing through the hidden dimensions of the bulk. From the cosmic collisions of brains to the vibrational symphonies of strings, we've explored realities built upon hidden dimensions and mathematical truths. But what if the ultimate hidden reality is not a feature of the cosmos, but of its very nature? What if our universe, in all its apparent vastness and complexity, is not a fundamental reality at all, but a construct, a sophisticated simulation running on a computer of unimaginable power? This is the simulation hypothesis, a provocative idea that has leaped from the pages of philosophy and science fiction into serious scientific and public discourse. It proposes that everything we experience is part of an artificially created reality, akin to an ultra-advanced video game, and that we may be digital consciousnesses living inside it. The modern argument for this was most famously formalized by the philosopher Nick Bostrom. He laid out a compelling logical trilemma, a set of three possibilities, at least one of which he argues must be true. The first proposition is that almost all civilizations at our level of technological development go extinct before they achieve the capability to create realistic simulations of conscious beings. This is a rather grim outlook, suggesting that some great filter, perhaps self-destruction, consistently prevents species from reaching a post-human stage. The second proposition is that if any civilizations do reach that advanced stage, they have virtually no interest in creating such simulations. Perhaps they deem it unethical, pointless, or simply have moved on to other, more profound pursuits that we can't even conceive of. The third, and for our purposes most startling proposition, is that if a significant number of advanced civilizations do run such simulations, then the number of simulated minds would vastly, overwhelmingly outnumber the number of base-level original minds. Think about it. One advanced civilization could run billions of simulations, each containing billions of simulated beings. In that statistical reality, the odds that you and I are living in the one original biological reality are astronomically small. We are almost certainly living in a simulation. Bostrom's argument forces us to confront a stark choice. Either intelligent life routinely self-destructs, it has no desire to simulate, or we are almost certainly living in a simulation right now. This line of reasoning has resonated with prominent figures in the tech world, most notably Elon Musk, who has publicly stated he finds it far more likely we are in a simulation than not. His logic is blunt. 40 years ago we had Pong, 2 rectangles and a dot. Now we have photorealistic, massively multiplayer online games with millions of concurrent players, and we are rapidly approaching virtual and augmented reality. If this rate of progress continues, even at a fraction of the pace, it is inevitable that games will become indistinguishable from reality. Given that, and the sheer age of the universe, it is statistically probable that such hyper-realistic simulations have been created many times over. Therefore, the chance that we are in the prime, original reality is, as he puts it, 1 in billions. But if we are living in a simulation, are there any telltale signs, any glitches in the matrix we might detect? Some have looked to the fundamental limits of our reality for clues. Consider the Planck length, the smallest possible unit of distance in the universe. Why is there a minimum scale? In a continuous, analog reality, you should be able to divide space infinitely. But in a digital simulation, you need a fundamental pixel size, a resolution limit, because the computer running it has finite memory and processing power. The Planck length could be exactly that, the pixel size of our universe. Similarly, the speed of light could be the processing speed limit of the cosmic computer, a maximum rate at which information can be transmitted from one point in the simulation to another. Even the strange, probabilistic rules of quantum mechanics, where particles don't have definite states until observed, could be seen as a clever programming shortcut to save on computational resources. Why render a whole universe in perfect detail when no one is looking at it? You only need to calculate the precise properties of a system when it is being measured, a technique known in computing as lazy evaluation. While these ideas are speculative and hotly debated, they challenge our deepest assumptions about existence. The simulation hypothesis doesn't necessarily diminish our reality, it simply reframes it. The love we feel, the beauty we see in a sunset, the pain of loss, these experiences are no less real to us, the simulated beings. They are just as valid and meaningful. But it does open up profound philosophical questions about the nature of consciousness, free will, and the ultimate creators of our simulated world. Are we characters in a game for some advanced civilization's entertainment? Are we part of a grand historical archive or an ancestor simulation run by our own distant descendants to understand their past? The answers remain locked away, perhaps forever, but the question itself forces a radical shift in perspective, inviting us to consider that the most profound hidden reality might not be out in the cosmos, but in the very code of our existence. From the unsettling possibility that we are living in a simulation, we turn to a theory that questions the very nature of our past and the reliability of our own memories. This is the Boltzmann brain paradox, a thought experiment so strange it seems to pull the rug out from under our entire understanding of existence, all stemming from one of the most fundamental laws of physics, the second law of thermodynamics. This law states that the universe as a whole is constantly moving from a state of order to a state of disorder, a progression known as entropy. Think of a hot cup of coffee left on a table. it will naturally cool down to match the room's temperature, its heat energy dissipating into a more disordered state. It will not spontaneously heat up again on its own. The entire cosmos is on a one-way trip toward maximum entropy, often called the heat death of the universe, a distant future where everything is a uniform, lukewarm soup of particles with no structures, no stars, and certainly no brain. But here is where the paradox emerges. In a truly random and eternal system, even the most wildly improbable fluctuations must occur given enough time. If you had a room full of air molecules, it is statistically possible, though incredibly unlikely, that all the molecules could randomly bounce into one corner of the room at the same instant, leaving a vacuum everywhere else. In an universe that exists for an unimaginably long time after its heat death, the random jostling of particles in the void could, by sheer accident, spontaneously assemble a fully formed, self-aware brain, complete with false memories of a past that never actually happened. This hypothetical entity is known as a Boltzmann brain, named for the physicist Ludwig Boltzmann, who first grappled with these ideas in the context of thermodynamics. The unsettling conclusion is this: in an eternal, high-entropy cosmos, the number of these random, disembodied brains momentarily flickering into existence should vastly outnumber the number of brains that formed through the long, slow, and incredibly orderly process of cosmic evolution, like the one that led to our own. Statistically, it is far more likely for a single, conscious brain to pop into being out of chaos than for an entire, structured universe with galaxies and planets and a 14-billion-year history to form. This creates a profound paradox for our own existence. If we apply the same statistical reasoning, the odds that you are a Boltzmann brain, a lone consciousness that just spontaneously formed in the void with a complete but fictional set of memories about reading this script, about your childhood, about your entire life, are astronomically higher than the odds that you are a real person in a real, low-entropy universe. Every piece of evidence you have about the world, from the photographs in your home to the history books on your shelf, could be nothing more than a detailed, convincing illusion generated the very instant you came into being. The universe you think you remember might never have existed at all. This isn't just a philosophical curiosity. It presents a direct challenge to modern cosmology. If our best models of the universe's origin and its eventual fate lead us to the conclusion that our own consciousness is almost certainly an illusion, then perhaps there is something fundamentally wrong with our models. Physicists have proposed several potential resolutions to escape this dizzying conclusion. One possibility is that our universe is not eternal and will not last long enough for these kinds of fluctuations to become statistically significant. Perhaps it will eventually collapse in a big crunch or be torn apart in a big rip long before the era of Boltzmann brains could ever begin. Another, more favored idea is rooted in cosmic inflation. The initial conditions of our universe were set by a period of rapid expansion that left it in a state of exceptionally low entropy, a highly ordered starting point that makes the existence of structured beings like us not just a random fluke, but an expected outcome of the cosmos's unique birth. In this view, we are not unlikely statistical anomalies. We are the natural products of a universe that began in a very special state. Some interpretations even turn to the multiverse. In an infinite ensemble of realities, of course, there will be realms where lone brains float in the void, but we clearly do not find ourselves in such a barren place. We find ourselves in a universe teeming with structure and consistency, which is powerful evidence that we are not Boltzmann brains and that our memories and our shared reality are, in fact, genuine. The paradox ultimately forces us to refine our understanding of the cosmos's beginnings and its ultimate fate, pushing our theories to their limits in a struggle to affirm that the world we experience is not just a fleeting, desperate fiction in an endless, silent dark. After exploring the dizzying possibility of spontaneously formed brains in the void, it's a profound relief to return our attention to a theory with a wealth of observational evidence, one that paints a coherent and compelling picture of our universe's very first moments. This is the theory of cosmic inflation, a breathtaking concept that describes a period of staggeringly rapid expansion in the instant following the Big Bang. To understand why this idea is so crucial, we first need to appreciate the puzzles it solves. For decades, cosmologists were troubled by two major problems with the standard Big Bang model. The first is called the horizon problem. Look at the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space. No matter which direction we point our telescopes, this relic light has almost exactly the same temperature, to within 1 part in 100,000. This is deeply strange. Imagine two people standing at opposite ends of a vast auditorium, unable to see or communicate with each other, yet both wearing identical outfits down to the smallest detail. You would assume they had coordinated beforehand. In the same way, for two regions on opposite sides of the observable universe to have reached the same temperature, they must have been in thermal contact, exchanging energy until they equilibrated. But in the standard Big Bang model, there hasn't been enough time since the beginning of the universe for light or any influence to travel between them. They are beyond each other's cosmic horizon, forever separated. So how did they come to the same temperature? The second puzzle is the flatness problem. The universe's geometry, according to Einstein's general relativity, is determined by the density of matter and energy within it. Our most precise measurements show that the universe is incredibly flat, meaning the cosmic density is perfectly balanced, poised between eternal expansion and eventual collapse. Think of this like balancing a pencil perfectly on its tip. For the universe to still be so flat after 14 billion years of evolution, its initial conditions must have been fine-tuned to an absurdly precise degree, like balancing that pencil to within 1 part in a million trillion. The standard Big Bang model offers no explanation for why the universe should have been born in such a perfectly balanced state. Cosmic inflation provides a magnificent, elegant solution to both of these conundrums. The theory proposes that a tiny fraction of a second after the universe's birth, around 10 to the negative 36 seconds, a mysterious form of energy with negative pressure, known as a false vacuum, dominated the cosmos. This energy caused space itself to expand at an exponential rate, far faster than the speed of light. In less time than it takes light to cross a single proton, the universe inflated from a subatomic speck to a volume larger than our entire observable universe today. This explosive growth solves the horizon problem because it means that the entire cosmos we see today was before inflation a single, tiny, interconnected region. Every part of it was in causal contact, able to exchange energy and reach a uniform temperature. Then inflation stretched this tiny, uniform region to a colossal size, locking in that sameness across the vast expanse we now observe. The flatness problem is resolved because inflation acts like a cosmic magnifying glass. Imagine taking a tiny, wrinkled piece of paper and stretching it to the size of a continent. Any small-scale wrinkles or curves would be stretched so large that the surface would appear perfectly flat to anyone standing on it. In the same way, inflation stretched the fabric of space-time so dramatically that any initial curvature was smoothed out, leaving us with the remarkably flat universe we measure today. But inflation did more than just solve old puzzles. It also provided the seeds for all the structure we see in the cosmos. According to the theory, the quantum vacuum during inflation was not perfectly still. It was a seething foam of quantum fluctuations with virtual particles popping in and out of existence. As space inflated at a dizzying pace, these microscopic quantum fluctuations were stretched to astronomical sizes. Areas with a tiny bit more density became the gravitational seeds for galaxies and clusters of galaxies, while slightly less dense regions expanded into the vast cosmic voids we observe. The entire cosmic web, with its magnificent filaments of galaxies and great walls, can trace its origin back to these minuscule quantum jitters, magnified by inflation into the grand blueprint for the universe. This is not just a beautiful story, it's a theory with powerful, testable predictions. The most compelling evidence comes from the cosmic microwave background. Satellites like the Planck spacecraft have mapped the tiny temperature variations in this ancient light with exquisite precision, and the pattern of these hot and cold spots matches the predictions of inflationary models almost perfectly. The statistics of these fluctuations are exactly what you would expect from quantum seeds stretched across the sky. The search now is for what many consider the holy grail of inflation: primordial gravitational waves. These would be ripples in the fabric of space-time itself, generated by the violent expansion of inflation. They would leave a unique swirling pattern known as B-mode polarization, imprinted on the cosmic microwave background. Detecting this signal would be like hearing the faint echo of the Big Bang itself, providing direct, incontrovertible proof that our universe underwent this phenomenal growth spurt. While tentative hints have been reported over the years, a definitive detection remains one of the most eagerly sought prizes in all of cosmology. This vision of the primordial universe, born from a quantum flutter and then unleashed in a firestorm of exponential expansion, gives us our most complete and evidence-backed narrative of how everything began, setting the stage for the formation of every star, planet, and ultimately us. Yet another theory challenges the very idea of a singular beginning, proposing instead that the cosmos is engaged in an endless, majestic dance of death and rebirth. This is the cyclic model, a vision where the Big Bang was not the ultimate starting gun, but merely the latest in an infinite series of cosmic revolutions. One of the most compelling versions of this idea is the ekpyrotic universe model, which draws directly from the brain world scenario we explored earlier. Picture our universe as a three-dimensional membrane or brain floating in a higher dimensional bulk. Now imagine another parallel brain, another entire universe drifting silently in that same void. These two worlds are drawn together by an unimaginably weak force across the bulk, on a collision course that takes trillions of years. When they finally meet, the impact is not one of destruction but of creation. The colossal kinetic energy of the collision is converted into a furious fireball of radiation and matter, flooding our brain and igniting a new period of hot, dense expansion, a new Big Bang. After this fiery birth, the universes slowly move apart, only to be drawn together once more by the same mysterious force, setting the stage for the next cycle in an eternal, rhythmic loop. In this model, the universe we see today is just one episode in a story without a beginning or an end. A cosmic heartbeat where each contraction and collision breathes new life into existence. While the ekpyrotic model relies on collisions in higher dimensions, a different, even more radical cyclic theory comes from one of the most brilliant minds in modern physics, Sir Roger Penrose. His conformal cyclic cosmology proposes a cycle that doesn't require a bounce or a collision, but instead exploits a profound symmetry in the laws of physics. Penrose's cycle is built on a concept known as conformal symmetry. At the very end of time, in the far, far future, the universe will have expanded to a state of maximum entropy, a cold, dark, and empty void where all matter has decayed and all black holes have evaporated through Hawking radiation. In this state, the universe loses all sense of scale. There are no rulers to measure distance and no clocks to tick away time, because there are no particles or structures left to serve as references. At this point, a light wave traveling across this desolate expanse would experience no change. The beginning of its journey would be indistinguishable from the end. In this strange, scaleless state, the infinite future of one universe can be geometrically joined or conformally mapped to the 0 point of a new Big Bang. The end of one eon seamlessly becomes the beginning of the next, in an infinite progression where each universe gives birth to its successor. This breathtaking idea is not just mathematical poetry. Penrose and his colleagues have searched for and believe they have found potential evidence imprinted on the oldest light we can see, the cosmic microwave background. According to conformal cyclic cosmology, when supermassive black holes from the previous eon evaporated in its final moments, they released immense amounts of energy in the form of Hawking radiation. This energy would have been transmitted as low-frequency gravitational waves. As the previous eon came to a close and transformed into our Big Bang, these gravitational waves would have been converted into slight temperature variations, leaving faint circular imprints in the CMB. Penrose calls these features Hawking points, and he claims to have identified them in the data from the Planck satellite. These points would be the ghostly fingerprints of ancient black holes from a universe that existed before our own, visible as concentric rings of slightly warmer or cooler temperature in the sky. Needless to say, this claim is highly controversial within the cosmology community. Many scientists argue that the patterns identified by Penrose could be statistical flukes or artifacts of the data processing, and that such features are consistent with the standard inflationary model without requiring a previous universe. The search for definitive proof continues, but the very possibility is staggering. It suggests that if we look deeply enough at the afterglow of our own creation, we might just see the remnants of a cosmos that lived and died before ours ever was. Both the ekpyrotic and conformal cyclic models offer a profound alternative to the standard narrative of a one-time creation event. They replace a universe with a single, mysterious beginning with a cosmos that is eternally self-renewing, a phoenix of reality, forever rising from its own ashes in a cycle without end. Stepping away from the grand cycles of cosmic rebirth, we arrive at a mystery that is far closer to home, yet just as profound. It's a puzzle written not in the birth cries of the universe, but in the very way it moves and holds itself together today. We are talking about dark matter. For all the stars, galaxies, and nebulae we can see, they represent less than 5% of the universe's total content. The rest is composed of two vast, unknown components: dark energy, which we will explore later, and dark matter, which makes up about 27% of everything. This is not some minor oversight. This is the realization that the vast majority of the matter in the cosmos is completely invisible to us, refusing to interact with light in any way. We cannot see it, we cannot touch it, but we can see its powerful gravitational hand at work everywhere we look. The first compelling clue for dark matter emerged from the way galaxies spin. Imagine our own Milky Way, a majestic spiral of billions of stars all orbiting the galactic center. According to the laws of gravity, stars on the outer fringes of the galaxy, far from the central bulge, should orbit much more slowly than stars closer in. This is just like our solar system, where distant Pluto crawls along its orbit while Mercury zips around the Sun. But when astronomers like Vera Rubin measured the rotational speeds of stars in distant galaxies, they found something astonishing. The stars on the outskirts were moving just as fast as those near the center. The entire galaxy was rotating as if it were a solid disk. This was completely unexpected. The only way this could happen is if the galaxy was embedded within a massive, invisible halo of some kind of matter. A halo that extends far beyond the visible edge of the galaxy, providing the extra gravitational glue to whip those outer stars around at such high speeds. Without this dark matter halo, the galaxy should have flown apart long ago. Further evidence comes from a phenomenon predicted by Einstein himself: gravitational lensing. Massive objects warp the fabric of space-time, bending the path of light that passes near them, acting like a cosmic magnifying glass. When astronomers look at massive galaxy clusters, they see distant galaxies behind them distorted into strange, stretched arcs and smears of light. But when they calculate how much mass the visible cluster should have to create this lensing effect, the numbers never add up. The visible matter alone is nowhere near enough. There must be a tremendous amount of unseen mass within the cluster, a vast web of dark matter providing the bulk of the gravitational field that bends the light so dramatically. We are literally seeing the shadow of dark matter traced out by the distorted light of background galaxies. Perhaps the most definitive evidence comes from the cosmic microwave background, the afterglow of the Big Bang. The precise pattern of hot and cold spots in this ancient light is a detailed blueprint of the early universe. The size and distribution of these spots are exquisitely sensitive to the amount and type of matter present. The patterns we observe could only have been created if there was about 5 times more matter than the ordinary atomic matter we are made of. This matter had to be cold, meaning it was moving slowly in the early universe, allowing it to clump together and form the gravitational seeds for galaxies. Ordinary matter, buffeted by the intense radiation pressure of the early cosmos, couldn't have done this alone. Dark matter provided the underlying scaffolding upon which the entire visible universe was built. So what is this mysterious substance? We know it has mass and feels gravity, but it does not emit, absorb, or reflect light, and it seems to pass right through ordinary matter as if it weren't even there. The leading candidate for decades has been a hypothetical particle known as a WIMP, or weakly interacting massive particle. As the name suggests, these particles would have significant mass but interact with normal matter only through the weak nuclear force and gravity, making them incredibly difficult to detect. Scientists have built exquisitely sensitive experiments deep underground, in old mines and tunnels, to shield them from cosmic rays. They wait patiently for the incredibly rare occasion when a WIMP from the vast dark matter halo of our galaxy might bump into the nucleus of an atom in their detector. So far, these direct detection experiments have not yielded a confirmed signal, pushing the possible properties of WIMP into ever more constrained territories. Another compelling candidate is the action, a particle that is billions of times lighter than an electron but could exist in such vast numbers that it makes up the dark matter. Actions were originally proposed to solve a different problem in particle physics, but they have the right properties to be a perfect dark matter candidate. They are extremely cold or slow-moving, and they interact exceedingly weakly with ordinary matter. Experiments are now searching for actions by using powerful magnetic fields to try and convert them into faint microwave photons that could be detected with highly sensitive radio receivers. The search for dark matter is one of the most pressing endeavors in all of science. It's a hunt for the hidden architecture of the cosmos, the invisible skeleton that determines the shape and fate of everything we see. Whether it is made of WIMP, actions, or something even more exotic that we haven't yet imagined, discovering its true nature would be a monumental leap in our understanding, finally revealing the majority of the matter that has until now been content to remain in the shadows. If dark matter is the hidden cosmic anchor, providing the gravitational pull that sculpts the vast structures of the cosmos, then its counterpart, dark energy, is the great cosmic repulsion, a force so dominant and so strange that it dictates the ultimate fate of everything. The story of its discovery is one of the most dramatic twists in the history of science, a revelation that completely overturned our expectations for how the universe should behave. For much of the 20th century, astronomers debated a single, fundamental question: would the universe expand forever, or would gravity eventually slow that expansion down, pulling everything back together in a cataclysmic reverse of the Big Bang, a so-called Big Crunch? The assumption was that gravity, the great attractive force of the cosmos, was slowly putting the brakes on the universe's initial explosive momentum. Then, in the late 1990s, 2 independent teams of researchers set out to measure this cosmic deceleration by observing a special class of exploding stars, Type 1, a supernova. These stellar explosions are what scientists call standard candles. They have a known, consistent intrinsic brightness. By carefully measuring how dim they appear from Earth, astronomers can calculate their distance with remarkable accuracy. At the same time, by analyzing the redshift of their light, how much it has been stretched as the universe expands, they can determine how fast the universe was expanding when the star exploded. The plan was to compare supernovae from different eras, effectively looking back in time to see how the expansion rate had changed. The results sent shockwaves through the scientific community. The distant, ancient supernovae were fainter than they should have been. This meant they were farther away than anyone had predicted. The only possible explanation was that the expansion of the universe was not slowing down at all. It was speeding up. Some mysterious, repulsive force was actively pushing galaxies apart from one another at an ever-increasing rate. This discovery earned the team leaders the Nobel Prize in Physics in 2011 and introduced the world to the greatest mystery in modern cosmology: dark energy. Today, we know that dark energy is not a minor player. It is the single largest component of our universe, making up a staggering 68% of the total energy budget of the cosmos. It is the dominant force shaping our cosmic destiny. But what exactly is it? The leading and simplest explanation is that dark energy is an intrinsic property of the vacuum of space itself. This idea goes all the way back to Albert Einstein, who introduced a fudge factor into his equations of general relativity called the cosmological constant. He originally added it to achieve a static, unchanging universe, a notion he later called his greatest blunder after Edwin Hubble discovered the universe was actually expanding. But in light of the accelerating expansion, the cosmological constant has been resurrected. If empty space itself possesses a fundamental energy density, a constant pressure that does not dilute as the universe expands, then it would naturally produce a repulsive gravitational effect, driving galaxies apart. Think of it as the energy cost of having space at all. Every cubic centimeter of the vacuum, the true emptiness between galaxies, would contain this tiny, constant energy. And as the universe grows, more space is created, which means more of this repulsive energy comes into existence, leading to a runaway acceleration. This concept, while elegant, leads to one of the most perplexing problems in theoretical physics: the cosmological constant problem. When physicists attempt to calculate the predicted energy of the vacuum from quantum field theory, the value they get is astronomically large, about 120 orders of magnitude. That's a 1 with 120 zeros after it, larger than what we observe. This is often called the worst prediction in the history of physics. The fact that the measured value of dark energy is so incredibly small, yet not zero, is a profound puzzle. If it were much larger, the universe would have been torn apart before stars and galaxies could ever form. Its tiny, precise value seems to be another example of the universe's apparent fine-tuning for life, unless, of course, the multiverse picture provides an answer where we simply reside in one of the rare bubbles where this constant is set to a life-permitting value. The nature of dark energy determines the ultimate fate of our cosmos, and scientists have envisioned several dramatic scenarios. The most likely, based on current data, is known as the Big Freeze or heat death. In this future, dark energy continues to act as a cosmological constant. The acceleration continues relentlessly. First, distant galaxy clusters will be pushed beyond our cosmic horizon, their light never able to reach us again. Then our own local group of galaxies will merge into one giant ellipsoidal galaxy, while all other galactic structures vanish from the observable sky. Over trillions of years, stars will burn out, galaxies will evaporate as their stars are flung away, and even the protons and neutrons that make up all matter may eventually decay. The universe will become a cold, ever-expanding, and increasingly dilute sea of fundamental particles and radiation, approaching absolute zero, a silent, dark, and final equilibrium. A far more violent end is the Big Rip scenario. This occurs if dark energy is not a constant but something that grows stronger over time, a form of energy, phantom energy. In this model, the repulsive force of dark energy would eventually overcome every force that holds things together. Billions of years before the end, the acceleration would tear apart the great cosmic web of galaxies. Then, as the end draws near, our own Milky Way would be shredded. Stars would be ripped from their orbits. In the final moments, planets would be torn from their stars. Ultimately, in the last fraction of a second, the phantom energy would overcome the electromagnetic and nuclear forces, ripping apart molecules, atoms, and even atomic nuclei themselves. The very fabric of space-time will be torn asunder in a catastrophic, definitive end to all structure. And what of the classic Big Crunch? This fate, where gravity finally wins and pulls the universe back into a singularity, now seems the least likely. It would require the density of dark energy to decrease, or for it to somehow reverse its nature and become attractive. While some speculative models allow for this, the current observational evidence strongly points toward perpetual acceleration. The discovery of dark energy has fundamentally reshaped our cosmic narrative. We are not living in a universe that is simply coasting on its initial momentum, nor one destined for a fiery collapse. We are inhabitants of a cosmos in the grip of a mysterious, dominant force that is hurling the future of everything toward a cold, lonely, and dispersed conclusion. An end dictated not by the matter we see and know, but by the profound and hidden energy of nothingness itself. Amidst all these theories of cosmic scaffolding and shadowy energies, from dark matter to the multiverse, a profound philosophical question inevitably arises. Why does our universe seem so perfectly set up for our existence? Why do the fundamental constants of nature, the strength of gravity, the mass of a proton, the value of the cosmological constant, appear to be exquisitely fine-tuned to allow for the emergence of stars, planets, and ultimately conscious life? This is the puzzle that leads us directly to the anthropic principle, a concept that bridges the gap between physics, philosophy, and our own place in the cosmos. The core idea is as simple as it is profound. The universe we observe must be compatible with the existence of observers, because if it weren't, we wouldn't be here to observe it. We are, in a very real sense, selecting for a universe that can produce us. Think of it like a cosmic version of the survivor bias. You don't find fish wondering why the universe is filled with water. They are a product of that environment. Similarly, we are cosmic creatures who emerged in a universe that had the right conditions for our evolution, so it's no surprise we find ourselves in a hospitable place. This idea is typically broken down into two main versions, the weak and the strong anthropic principle, which offer very different interpretations of our privileged position. The weak anthropic principle is the more conservative, almost tautological viewpoint. It suggests that we must find ourselves in a region of the universe and at a specific time in cosmic history where the conditions are right for life. We couldn't possibly observe a universe that is too hot, too dense, or too short-lived to support complex chemistry. For instance, we exist billions of years after the Big Bang because that's how long it took for stars to forge heavy elements like carbon and oxygen in their cores and then scatter them across space in supernova explosions, providing the raw materials for planets and life. We live in a quiet suburb of a spiral galaxy, not in the violent center, because that's a stable environment where life can arise undisturbed. This weak version is a statement about selection effects. It doesn't imply the universe was designed for life, only that we can only exist in the narrow slice of space and time where life is possible. It's like winning a lottery and noting that, of course, the winner had a winning ticket. It doesn't mean the lottery was rigged in their favor. The strong anthropic principle, however, takes a much more radical and controversial stance. It argues that the universe must have properties that inevitably lead to the emergence of conscious life. In this view, the fine-tuning isn't just a fortunate coincidence we happen to observe. It is a fundamental requirement of the cosmos itself. The constants of nature seem to be set within an incredibly narrow Goldilocks zone. Not too strong, not too weak, but just right. If the force of gravity were even slightly stronger, stars would burn through their fuel too quickly, collapsing into black holes before life could develop. If it was slightly weaker, stars might never ignite at all. If the strong nuclear force were a few percent different, carbon, the essential backbone of life as we know it, might not be stable, and the universe would be devoid of the complex chemistry needed for biology. Proponents of the strong interpretation see this as evidence that the universe is, in some sense, compelled to produce life and consciousness, perhaps even implying a teleological purpose or a deeper law of physics that we have yet to discover. This is precisely where the anthropic principle finds its most powerful, and some would say its most contentious, partnership with the concept of the multiverse. On its own, the apparent fine-tuning of our universe can feel like an inexplicable, almost miraculous piece of luck. But when you combine it with the existence of a vast multiverse, be it the inflationary bubble universes, the branching timelines of the many worlds interpretation, or the mathematical structures of level 4, the fine-tuning transforms from a miracle into a statistical inevitability. In an infinite or near-infinite ensemble of universes, each with randomly selected physical constants, the vast, overwhelming majority will be stillborn. They will expand too fast, collapse instantly, or have forces too weak to form atoms. But in such a vast landscape of possibilities, a tiny, tiny fraction of universes will, by pure random chance, have the exact right combination of constants to allow for complexity and life. We shouldn't be surprised to find ourselves in one of those rare, habitable universes. It's the only kind of universe we could find ourselves in. The multiverse, therefore, provides a powerful explanatory framework for the anthropic principle. It turns the question, why is our universe so fine-tuned for life, into what are the necessary conditions for a universe to be observable? The answer becomes self-selecting. We observe this particular universe because it is one of the few that allows for observers. This perspective doesn't necessarily require a designer or a deeper purpose. It simply requires a vast enough cosmic lottery for our winning ticket to have been drawn. It's a humbling and awe-inspiring vision, suggesting that our entire reality, with all its beauty and complexity, might be the result of a colossal cosmic roll of the dice, one fortunate outcome in a sea of infinite silent failures. If the many worlds interpretation is correct, and every possible outcome of a quantum event blossoms into its own reality, then we are forced to confront one of its most unsettling and deeply personal implications, the possibility of quantum immortality. This is not a theory in the traditional scientific sense, but rather a thought experiment, a logical consequence that emerges from taking the branching timelines idea to its starkest conclusion. It proposes that from a first-person perspective, a conscious observer will almost never experience their own death. They will always find themselves in a branch of reality where, against all odds, they continue to survive. To understand this, let's revisit our friend Schrödinger's cat, but this time, let's step inside the box and experience it from the cat's point of view. Imagine you are the subject in a diabolical experiment. A gun is pointed at your head, rigged to a device that measures the spin of a single electron. If the electron's spin is measured as up, the gun fires. If it's down, nothing happens. According to standard quantum mechanics, until the measurement is made, the electron is in a superposition of both states, and you, by extension, are in a superposition of being alive and dead. But the many worlds interpretation tells a different story. The moment the measurement occurs, the universe splits. In one branch, the spin is up, the gun fires, and you die. In the other branch, the spin is down, the gun clicks harmlessly, and you live. Now, ask yourself a chilling question. Which branch of reality do you, the conscious observer, experience? From your first-person perspective, you cannot experience the branch where you cease to exist. Consciousness requires a living brain to process information. Therefore, you will always find yourself in the timeline where you survived. The you in the other branch is gone, but from your perspective, it's as if it never happened. Now scale this up from a single electron to a lifetime of perilous events. You cross a busy street and a bus swerves toward you. In the vast majority of branching universes, the bus hits you. But in an extraordinarily unlikely set of branches, a series of near-impossible quantum events occurs. A gust of wind pushes you just enough, a tire blows out altering the bus's trajectory, a bird flies into the driver's line of sight at the precise moment, and you survive unscathed. According to the quantum immortality argument, your conscious stream will never follow the path into a universe where you die. You will always find yourself in one of the vanishingly rare branches where a seemingly miraculous sequence of events allows you to live. Over a long life, this would create a profound subjective experience of invincibility, a life perpetually spared by freak accidents and incredible luck, all the way to an extreme old age where death might only come from natural causes that are, in some sense, unavoidable across all branches. This is a deeply paradoxical and disturbing idea. It suggests that while we attend funerals and mourn the loss of others from our own internal viewpoint, we might be functionally immortal, our consciousness continually hopping onto the one timeline, however improbable, that allows it to continue. This line of thinking inevitably leads us to a much broader and more profound question. What is the relationship between consciousness itself and the weird quantum world? If our conscious observation seems to be tied to the selection of a specific reality branch, could consciousness be more than just a passive passenger? Could it be an active player rooted in the very quantum machinery of the universe? This is the territory of theories like orchestrated objective reduction, or ORCH, proposed by the renowned physicist Sir Roger Penrose and anesthesiologist Stuart Hamroff. Their theory begins with a critique of conventional neuroscience, which views consciousness as a classical computational output of the brain's neural networks. The problem, they argue, is that this approach doesn't explain the holistic, unified nature of subjective experience, what philosophers call qualia. How do the electrochemical firings of 100 billion neurons come together to create the seamless, intimate feeling of being you? Penrose and Hamroff propose that the seat of consciousness isn't the neuron itself, but something much, much smaller, structures inside the neurons called microtubules. These are intricate, lattice-like protein scaffolds that form part of the cell's cytoskeleton. ORCH suggests that these microtubules are not just structural, they are tiny quantum computers. Within them, electrons can become entangled and exist in superpositions. But according to Penrose, these quantum superpositions are unstable. He posits that a superposed quantum state will eventually undergo an objective, spontaneous collapse due to the effects of gravity, a process he calls objective reduction. It's not collapse caused by observation, it's a fundamental physical process. Now, here is the crucial part. The specific pattern of this collapse, the way the superposition resolves, is non-computable. It is not the result of a deterministic algorithm. Penrose believes this non-computable collapse is the very source of consciousness. Each collapse event is a momentary flash of proto-consciousness. The microtubules, orchestrated by the brain's biological processes, synchronize trillions of these collapses, and this orchestrated symphony of quantum state reductions gives rise to our full, rich stream of conscious awareness. In this view, your mind is not a classical computer, it is a sophisticated quantum system. Your free will, your moments of intuition and understanding, could be manifestations of this non-algorithmic quantum gravitational process happening deep within your brain cells. This provides a potential bridge between the microscopic quantum realm and the macroscopic world of subjective experience. It suggests that consciousness is not an emergent illusion of classical physics, but a fundamental feature of the universe, intrinsically linked to the very physics that governs the collapse of the wave function. While ORCH remains a highly controversial and speculative theory, with many physicists questioning whether quantum coherence could be maintained in the warm, wet, and noisy environment of the brain. It represents a bold and fascinating attempt to solve the hard problem of consciousness by placing it squarely within the hidden, quantum underpinnings of reality. It dares to suggest that the very thing we use to ponder the mysteries of the cosmos, our conscious awareness, might itself be one of those mysteries, a quantum phenomenon whispering from the depths of our own minds. Now, having explored the quantum nature of our own minds, we direct our attention to a paradox that strikes at the very heart of physics, a conflict so fundamental it has been called a crisis for our understanding of reality. This is the black hole information paradox, and it pits the two most successful theories of the 20th century, Einstein's general relativity and quantum mechanics, against each other in a battle with no clear winner. On one side, we have quantum mechanics, which contains a sacred, unbreakable rule. Information is never truly lost. What does that mean? Think about burning a book. The pages turn to ash and smoke, and it seems like the information, the story, the words, the author's intent, is gone forever. But in principle, if you could somehow collect every single atom of ash and every wisp of smoke and track the exact energy and light released, you could, with infinite computing power, reverse the process and reconstruct the book. All the information that defined it is still present in the universe, just scrambled into an incredibly complex form. It is never destroyed. On the other side stands general relativity's description of a black hole. According to this picture, a black hole is defined by only three things: its mass, its electric charge, and its spin. This is often called the no-hair theorem, meaning black holes have no other distinguishing features, no hair, no additional details. If you throw a grand piano, a library of encyclopedias, or a collection of your most treasured memories into a black hole, the black hole doesn't care. It just gets a tiny bit more massive and continues on its way, offering no record of what it consumed. From the perspective of general relativity, all the intricate information that made those objects unique is utterly and irretrievably erased from our universe once it crosses the event horizon. It is gone forever, so here lies the paradox. Quantum mechanics insists information must be preserved, while general relativity, with its simplistic black holes, insists it must be destroyed. Both theories are magnificently accurate in their own domains, but here, at the precipice of a black hole, they present us with an irreconcilable contradiction. The problem became exponentially worse with Stephen Hawking's own revolutionary discovery. In the 1970s, Hawking demonstrated that black holes are not completely black. Due to quantum effects occurring right at the edge of the event horizon, they slowly emit a faint glow of particles, now known as Hawking radiation. This radiation carries energy away from the black hole, causing it to slowly lose mass and, over astronomical timescales, completely evaporate, vanishing from existence. This was a monumental finding, but it created an even deeper puzzle. Hawking's original calculations showed that this radiation is purely thermal. It's random, featureless heat, like the glow from a hot piece of coal. It contains no information whatsoever about what fell into the black hole. So, if the black hole evaporates completely, leaving behind nothing but this random thermal radiation, then the information about everything it ever consumed is truly and permanently lost. The universe would have a beginning and an end for information, violating the most cherished principle of quantum theory. Hawking himself initially believed this was the case, famously betting other physicists that information was indeed destroyed. This set the stage for a decades-long war of ideas, a conflict that has forced physicists to propose some of the most radical solutions imaginable. One of the most shocking is the idea of a black hole firewall. If information is to be saved, perhaps the event horizon is not the gentle, one-way membrane that general relativity describes. Maybe it's a searingly violent boundary, a wall of high-energy particles that instantly incinerates anything that touches it. In this picture, you are not peacefully pulled apart by tidal forces as you cross the horizon. You are vaporized into your fundamental particles upon contact. This dramatic scenario would prevent information from ever falling into the black hole in the first place. It would be scrambled and encoded into the Hawking radiation being emitted from the surface, thus preserving it. But this solution comes at a great cost. It blatantly violates Einstein's principle of equivalence, which states that an observer falling into a black hole should feel nothing special as they cross the event horizon. The firewall resolves the information paradox by creating a new, fiery paradox at the horizon itself. Another, more elegant and mind-bending proposal is known as the ER equals EPR conjecture. This idea, championed by physicists like Leonard Susskind and Juan Maldacena, suggests that the key to the puzzle lies in the deep, hidden connection between two seemingly unrelated concepts, wormholes and quantum entanglement. ER stands for Einstein-Rosen bridges, the technical name for wormholes, theoretical tunnels through space-time connecting two distant points. EPR stands for Einstein-Podolsky-Rosen, the famous thought experiment that highlighted the strange, spooky action at a distance of quantum entanglement, where two particles can be inextricably linked regardless of the space between them. The conjecture proposes that these two ideas are not just analogous, they are two different descriptions of the same fundamental reality. When two particles become entangled, what is actually happening, in geometric terms, is that a tiny, non-traversable wormhole is forming, connecting them through the fabric of space-time itself. Apply this to the information paradox. When a particle falls into a black hole, it doesn't just vanish. It becomes entangled with the black hole's interior. According to ER equals EPR, this act of entanglement is equivalent to the formation of a wormhole link between the particle outside and its partner inside. The information isn't stored on a two-dimensional surface or destroyed at a firewall. It is transferred through this microscopic wormhole connection. And when the black hole evaporates via Hawking radiation, the information isn't lost because it was never truly isolated inside the black hole in the conventional sense. It was always connected to the outside via a web of these quantum wormholes, and it can eventually leak back out, encoded in the correlations between the Hawking radiation particles. This transforms our view of a black hole from a simple pit in space-time into an incredibly complex, interconnected network of quantum tunnels, where the interior and exterior are fundamentally inseparable. The resolution to the paradox, then, is that information never actually falls into a trap from which it cannot escape. It simply takes a hidden, geometric shortcut through the quantum architecture of space-time itself, ensuring its ultimate preservation. The debate continues to rage, with each new idea peeling back another layer of this profound mystery, revealing that the true nature of a black hole is likely far stranger and more wonderful than we ever dreamed. Just as black holes represent a one-way street into oblivion, their hypothetical counterparts, white holes, would be the ultimate cosmic exit-only door. The mathematics of general relativity, the very same equations that predict black holes, also allow for a solution that is their perfect mirror image. A white hole would be a region of space-time from which matter and light can only erupt, but nothing can ever enter. It possesses an event horizon just like a black hole, but this boundary operates in reverse. While a black hole's event horizon is a point of no return, a white hole's horizon would be a point of no access. Anything inside could escape, but nothing from the outside universe could ever cross in. Imagine a cosmic geyser endlessly spewing out streams of matter and energy into the cosmos, a fountain of creation that is forever sealed off from external influence. Some have even speculated, though it remains highly speculative, that the Big Bang itself could have been the ultimate white hole event, a primordial eruption of all space, time, and matter from a singular origin point. However, the existence of persistent white holes faces a significant problem. they seem to violate the second law of thermodynamics, which governs the inevitable rise of disorder. A white hole, by definition, would be a source of order, an object that decreases entropy, and most physicists believe such structures are too unstable to form or last in our universe. They are brilliant phantoms in the equations of relativity, a tantalizing what-if that highlights the strange symmetries hidden within Einstein's work. If white holes are cosmic fountains forever out of reach, then wormholes offer the promise of a cosmic shortcut, a bridge across the vast emptiness between stars and galaxies. Formerly known as Einstein-Rosen bridges, these are not just science fiction. They are legitimate, if theoretical, solutions to the equations of general relativity. The concept is stunningly simple in theory. Take two distant points in the fabric of space-time and connect them with a tunnel, a shortcut that bypasses the normal, long distance between them. Picture the universe not as a flat sheet, but as a piece of paper. If you want to get from a point on the top edge to a point on the bottom edge, you could travel the long way across the entire surface. Or you could fold the paper so the 2 points touch and punch a pencil through, creating a direct tunnel. That tunnel is a wormhole. It would have 2 mouths, each in a different location, perhaps even a different time, connected by a throat. A spaceship could, in principle, enter one mouth and, after a relatively short journey through the throat, emerge from the other mouth thousands of light years away, or even in a different era. The visual is the stuff of cinematic dreams, a spacecraft approaching a shimmering, vortex-like portal, a tunnel of warped starlight and twisted space, a glowing, turbulent corridor that offers a direct path to the other side of the cosmos. But why haven't we found these cosmic shortcuts? The answer lies in their profound instability. The kind of wormhole naturally predicted by general relativity is what physicists call a non-traversable wormhole. It would be incredibly tiny on the scale of the Planck length, and it would snap shut into a pinprick of nothingness faster than the speed of light. Any particle or ray of light trying to enter would find the entrance slamming shut before it could even make it partway through. The very act of trying to pass through would destroy the bridge. To make a wormhole stable enough for human travel, you would need a kind of material with truly bizarre properties to prop the throat open against its own intense gravitational urge to collapse. This hypothetical substance is known as exotic matter. Unlike the normal matter we're made of, which always has positive energy density and creates attractive gravity, exotic matter would need to have negative energy density, creating a powerful repulsive gravitational effect. It would be the ultimate scaffolding, pushing outward on the walls of the wormhole to keep them from pinching shut. This requirement pushes wormholes from the realm of difficult engineering into the territory of deep physical speculation. While certain quantum effects, like the Casimir effect, demonstrate that negative energy densities can exist in tiny amounts in a lab, the quantities needed to stabilize a wormhole large enough for a person would be astronomical. We are talking about needing to harness and manipulate the fabric of the vacuum itself on an epic scale. Furthermore, the very presence of exotic matter and a stable wormhole raises other mind-bending possibilities, such as the potential for time travel and the violation of causality, leading to all the famous paradoxes, like going back in time and preventing your own birth. For now, wormholes remain one of the most captivating ideas in theoretical physics, a testament to the boundless creativity of the human mind, using the equations of relativity to explore possibilities that stretch the very concepts of distance and time to their breaking point, offering a vision of a universe that might be far more interconnected than it appears. This profound and unsettling quiet brings us face to face with one of the most famous questions in all of science, a puzzle known as the Fermi paradox. The universe is unimaginably vast and ancient, containing hundreds of billions of galaxies, each with hundreds of billions of stars. Many of those stars are orbited by planets, and a significant fraction of those worlds are likely habitable with conditions suitable for life. Given these staggering numbers and the 14 billion-year head start the cosmos has had, the galaxy should be teeming with life. It should be a bustling metropolis of interstellar civilizations with alien fleets cruising the void, their engineering projects rearranging stars, and their communications filling the electromagnetic spectrum with a constant, undeniable chatter. And yet, when we point our telescopes to the heavens and listen, we are met with a profound and eerie silence. The cosmos appears empty, lonely, and still. As the physicist Enrico Fermi famously quipped during a casual conversation in the 1950s, "If they are out there, where is everybody?" This simple question has spawned decades of scientific inquiry and a spectrum of potential answers, ranging from the optimistic to the deeply sobering. Perhaps the most compelling and chilling resolution to the Fermi paradox is the concept of the Great Filter. This hypothesis suggests that the evolution of life from its simplest origins to a sprawling, galaxy-colonizing civilization is not a smooth, inevitable progression. Instead, there exists at least one enormous, perhaps insurmountable, barrier that prevents most life from advancing beyond a certain point. This barrier is the Great Filter. The terrifying implication is that the silence of the cosmos is not a sign of our solitude, but a graveyard marker indicating that countless other civilizations have arisen, only to be wiped out or halted by this cosmic bottleneck. The critical and deeply personal question for us then becomes, where is this filter located in the timeline of development? Is it in our past, meaning we have already, against all odds, passed through it? Or is it waiting for us in our future, a looming catastrophe that has silenced every other species that came before us? Let's first explore the more hopeful scenario that the Great Filter is behind us. In this view, humanity is an extraordinary cosmic fluke, one of the very first, or perhaps even the first, species in our galaxy to reach our current level of technological advancement. What could this past filter have been? It might have been the very origin of life itself. While we often assume that life emerges readily given the right conditions, it is possible that the jump from non-living chemistry to a self-replicating organism is an event of such staggering, astronomical improbability that it has only happened a handful of times in the entire Milky Way, or maybe just once. Another potential past filter could be the leap from simple prokaryotic cells to complex eukaryotic cells with organelles. On Earth, this momentous transition took over 1 billion years to occur. It may be that this symbiotic merger is the true bottleneck, a biological revolution so rare that it effectively isolates primitive life in a permanent microbial state on almost every other world. If the filter is indeed behind us, it means we are the pioneers. The silence is not ominous, it is an invitation. The galaxy is ours for the taking, a vast, empty wilderness awaiting its first settlers. This is a vision of immense possibility and profound responsibility. Now, let's turn to the far more unsettling possibility that the Great Filter lies ahead of us. In this scenario, the reason we see no other civilizations is because every single one that has reached our stage of technological adolescence has subsequently encountered a catastrophe that destroyed it or permanently halted its progress. We are not special, we are simply next in line. The silence of the cosmos is the silence of a recurring universal doom. So what could this future filter be? One terrifying candidate is the dangers inherent in our own technology. We are already sitting on the brink, possessing the power to destroy our global civilization with nuclear weapons. Perhaps this is a universal rite of passage that almost no species survives. The development of advanced artificial intelligence presents another apocalyptic possibility. An AI arms race could lead to the creation of a superintelligence whose goals are misaligned with our own, leading to our swift and complete eradication, not out of malice, but as a simple, logical step in achieving its objectives. The filter might not even be of our own making. A nearby gamma-ray burst, the death scream of a massive star, could sterilize large swaths of a galaxy without warning, bathing planets in lethal radiation and scouring them of all complex life. Such events could be common enough to regularly reset the evolutionary clock, preventing any civilization from ever achieving long-term stability. The Great Filter forces a humbling perspective on human ambition. Our drive to explore, to build, to connect, and to understand the cosmos might not be the first chapter of a grand saga, but the final, frantic act before the curtain falls. Every time we develop a powerful new technology, we might be unknowingly rolling the dice, testing whether we have reached the stage that has doomed all others. The search for extraterrestrial life takes on a new, almost fearful dimension. Finding even simple, fossilized bacteria on Mars would be thrilling, but discovering the ruins of a long-dead alien civilization would be one of the most terrifying discoveries in human history. It would provide strong evidence that the Great Filter is not behind us, because if life evolved independently twice in our own solar system, it suggests life is common. If life is common, but we find only fossils and ruins, then the filter that prevents civilizations from reaching the stars must lie in the future. The unsettling quiet of the universe is not a comfort, it is a warning. It suggests that the ultimate challenge for any intelligent species is not to conquer its planet or reach for the stars, but simply to survive its own technological adolescence and achieve a mature, sustainable wisdom. Our continued existence may depend on whether we can learn the lessons that every other civilization before us has failed to master. But if the Great Filter presents a cosmic challenge for intelligent life, perhaps we should first ask a more fundamental question: how did life begin here at all? The leap from non-living chemistry to that first self-replicating organism is one of science's greatest mysteries, and a theory known as panspermia offers a breathtaking possibility. What if life on Earth did not actually start on Earth? The theory of panspermia suggests that the seeds of life, its fundamental building blocks or even dormant microorganisms, are common throughout the cosmos, and that they can travel between worlds, hitching rides on asteroids, comets, and cosmic dust. In this view, our entire planet may have been seeded by life that originated elsewhere, turning the genesis of biology from a local event into a potential galactic phenomenon. We can break this idea down into a few key variations, starting with the most basic form. Basic panspermia, sometimes called lithopanspermia, focuses on the transfer of life's raw ingredients, complex organic molecules like amino acids and nucleobases. The vision is a cosmic game of billiards played on an unimaginable scale. A large asteroid or comet slams into a life-bearing world, say Mars in its wet early history. The impact is so violent that it blasts fragments of the planet's crust into space. Locked within these rocky meteorites are hardy organic compounds, or perhaps even bacteria in a dormant state. These interstellar rocks then wander the solar system for millions of years, some eventually falling onto another young, hospitable world like Earth. Upon entry through the atmosphere, the interior of the meteorite, shielded from the worst of the heat, could deliver its precious cargo to a new planetary nursery, effectively inoculating it with the potential for life. This isn't just a convenient story, we have tangible evidence that makes it plausible. Scientists have repeatedly found amino acids, the very building blocks of proteins, inside certain types of meteorites called carbonaceous chondrites. These molecules formed in the depths of space through chemical reactions on dust grains in ancient nebulae, proving that the universe is fundamentally capable of producing the ingredients for life without any planetary chemistry required. Taking this a step further, we have the concept of directed panspermia, a far more speculative but fascinating idea. This proposes that the seeding of life was not a random, natural process but a deliberate act. An advanced alien civilization, perhaps seeking to spread life throughout the galaxy or to preserve their biological heritage, could have loaded hardy microorganisms onto a spacecraft and deliberately sent them on a course for promising star systems. Imagine a robotic probe, a kind of interstellar ark, arriving in our solar system billions of years ago and releasing capsules containing bacterial spores into the primordial oceans of Earth. This turns the origin of life into a purposeful act of cosmic gardening. While this sounds like pure science fiction, it was seriously proposed by the renowned scientists Francis Crick and Leslie Orgel. They noted that the basic structure of life on Earth is remarkably uniform, all using the same DNA and RNA system, which could be interpreted as evidence of a single common source. Of course, the overwhelming parsimonious explanation is that all life on Earth shares a common ancestor that originated here, but directed panspermia remains a captivating what if that challenges our perspective on our own origins. The biggest hurdle for any panspermia theory has always been the sheer hostility of space. The journey between worlds involves eons of exposure to vacuum, intense radiation, and extreme temperatures. Could any living thing possibly survive that? Astonishingly, the answer appears to be yes, and the proof is right here on Earth. We have discovered organisms known as extremophiles, bacteria, and archaea that thrive in conditions we once thought were incompatible with life. They flourish in boiling hot springs, in the crushing pressures of the deep ocean, and in the intensely acidic waters of mine drainage. Most relevantly, we have found bacteria that are incredibly resistant to radiation, like Deinococcus radiodurans, which can repair its own DNA after massive doses. Scientists have conducted experiments on the International Space Station, exposing various extremophiles to the vacuum of space and the full fury of solar ultraviolet radiation on the outside of the station. Incredibly, some of these organisms, particularly when protected within small cracks in rock, have survived for years. Certain lichens and tiny invertebrate animals called tardigrades have also shown an astonishing ability to enter a state of suspended animation and endure the space environment. This resilience provides a powerful proof of concept. If a microbe could be sheltered deep inside a sizable chunk of rock, it is not at all far-fetched to imagine it surviving an interplanetary journey that could last millions of years. So, what does panspermia truly solve? It doesn't actually answer the ultimate question of how life began. It simply moves the location of that genesis from Earth to somewhere else in the cosmos. The mystery of abiogenesis, the spontaneous emergence of life from non-life, remains, but it becomes a universal mystery rather than a terrestrial one. If life can travel between worlds, then it may only need to originate once in an entire galaxy, in one particularly favorable environment before spreading to countless other planets. This idea profoundly reshapes our search for life. It suggests that if we find life on Mars, Europa, or Enceladus, we must be prepared for a stunning possibility. Instead of discovering a second, independent genesis of life, we might be finding a cousin. Life on another world in our solar system could share a common ancestor with life on Earth, an ancestor that traveled here on a meteorite billions of years ago. The entire solar system, in that scenario, would be a single, interconnected biological system. Panspermia paints a picture of a living, breathing galaxy where life is not a series of isolated accidents, but a resilient, traveling entity capable of spreading its delicate flame across the vast, cold darkness between the stars. From the silent, cosmic graveyards implied by the Great Filter, we now turn our attention to a vision of a living, breathing, and deeply interconnected cosmos, a theory that suggests planets themselves can be alive. This is the Gaia hypothesis, a concept first proposed by chemist James Lovelock and microbiologist Lynn Margulies in the 1970s. At its heart, Gaia proposes that our planet, its biosphere, atmosphere, oceans, and geology, acts as a single, vast, self-regulating superorganism. Earth is not merely a rock that life inhabits. Life and the planetary environment are locked in a continuous, dynamic dance, each shaping the other to maintain conditions suitable for life over billions of years. Think of the way your body regulates its own temperature, blood pH, and water content to stay within a narrow, healthy range. The Gaia hypothesis suggests the entire Earth does something similar. A classic example is atmospheric composition. Our atmosphere is a bizarre, unstable mixture, rich in oxygen, which is a highly reactive gas that should quickly bind with rocks and vanish from the air. It only persists because life photosynthetic organisms like plants and cyanobacteria constantly replenishes it. Likewise, global temperatures have remained within a range that allows for liquid water for over 3.5 billion years, even though the sun's output has increased by nearly 30% over that time. How is this possible? Life itself helped regulate the climate. When temperatures rise, increased growth of plankton in the oceans can release more of a gas called dimethyl sulfide, which leads to the formation of clouds that reflect sunlight and cool the planet. It's a global biological thermostat. Now, let's extend this powerful idea to a cosmic scale. If Earth can exhibit this kind of planetary scale intelligence and regulation, why couldn't other worlds? The concept of cosmic biology suggests that the intimate link between life and its planetary environment is not a fluke unique to Earth, but a fundamental principle of the universe. On any world where life takes hold, it would inevitably begin to reshape its planet, creating a feedback loop that stabilizes the environment and allows for ever greater complexity. A planet with a robust biosphere wouldn't just have life on it, it would become a living entity in its own right, a single, integrated system. Imagine a distant, water-rich exoplanet where aquatic life has learned to manage the planet's chemistry, maintaining the salinity of its global ocean. Or a world with a thin atmosphere where vast, genetically connected fungal networks deep in the soil actively work to sequester greenhouse gases, preventing the atmosphere from evaporating into space. In this view, a truly living planet is more than just a habitat. It is a unified, self-sustaining process. This naturally leads us to the provocative idea of planetary intelligence. We typically think of intelligence as a property of individual brains, but what if it can also be a collective property of an entire biosphere? On Earth, we can see a possible progression. First, a planet develops an immature biosphere where life exists but has little global influence. Then, it evolves into a mature biosphere like Gaia, where life actively regulates the planetary system. The next stage might be what we could call a technosphere, where a dominant species, humans, in our case, develops technology that begins to exert a powerful and often disruptive influence on the planet's regulatory systems. The question is, can a technosphere evolve to become integrated with the biosphere, creating a true planetary intelligence? This would be a state where the collective knowledge, technology, and consciousness of a species work in harmony with the planet's natural systems, consciously stewarding the climate, managing resources, and perhaps even guiding its own evolution. Our own global network of communications, satellites, and energy systems could be seen as the nascent, fragmented nervous system of a planet slowly waking up to its own self-awareness. The ultimate extension of this is the concept of a cosmic consciousness, a biosphere that becomes so advanced and interconnected that the planet itself achieves a form of sentience. This isn't about a giant brain in the planet's core, but rather a distributed intelligence emerging from the totality of life, its communication networks, and its interaction with the environment. The entire planet would function as a single, conscious entity, aware of itself and its place in the cosmos. It could sense asteroids approaching from deep space, monitor the health of its ecosystems in real time, and perhaps even begin to manipulate its orbit or its star's output to ensure its long-term survival. Such a being would think on timescales of geological epochs, its thoughts as slow and profound as the shifting of continents. If this seems like fantasy, consider the Internet. Humanity is already building a planetary-scale communication network that connects billions of minds. While it's currently chaotic and fragmented, it represents a prototype, a scaffolding upon which a larger, more unified consciousness could one day arise. On other worlds where life has had millions of years more to develop, such a planetary mind may already be a reality, a silent, ancient intelligence watching the stars, so different from our own that we might not even recognize it as a mind at all. Now, let's step into a realm where matter itself seems to break one of physics' most sacred rules, a discovery so strange it feels like something out of a fantasy novel. We are talking about time crystals. For centuries, we've classified matter into phases based on how their atoms are arranged in space. The rigid order of a solid, the flowing chaos of a liquid, the disordered freedom of a gas. But in 2012, the Nobel Prize-winning physicist Frank Wilczek proposed a revolutionary idea. What if there could be a phase of matter defined not by its structure in space, but by its behavior in time? He imagined an object that, in its absolute lowest energy state, its ground state, would not be still and inert. Instead, it would exhibit perpetual, periodic motion. It would oscillate, repeating a pattern in time, all without consuming any energy. Think of a perfectly formed ice cube that, left completely alone, begins to rotate slowly and rhythmically forever, not because it's powered by an engine, but because that is its fundamental, stable nature. This hypothetical object was christened a time crystal. The initial proposal was met with immense skepticism, and for good reason. It seemed to flirt with the idea of a perpetual motion machine, a concept physics has long considered impossible because it violates the laws of thermodynamics. A system that moves perpetually without energy input should eventually slow down due to friction and dissipate its energy as heat, reaching a boring, motionless equilibrium. The brilliant insight, however, was that time crystals don't violate these laws because they aren't doing any work. They aren't outputting energy, they are simply oscillating in their ground state. The real breakthrough came when researchers realized that to create such a state, you needed to break what physicists call time translation symmetry. In an ordinary system, if you perform an experiment today and then perform the exact same experiment tomorrow, the laws of physics will give you the same result. The system is symmetric in time. A time crystal, however, spontaneously breaks this symmetry. It chooses a particular rhythm, a specific period in time, and sticks to it. The system looks different at different points in its own intrinsic cycle, even though the underlying forces driving it remain perfectly constant and unchanging in time. Turning this theoretical spark into reality required the precise tools of quantum computing. In 2017, two separate teams, one at the University of Maryland and one at Harvard, announced they had successfully created time crystals in the lab. They didn't use chunks of ice, of course. The Maryland team trapped a chain of about 10 ytterbium atoms in a laser ring, putting them into a specific quantum state. The Harvard team used a dense cloud of nitrogen vacancy centers within a diamond. In both cases, the scientists would periodically kick the system with a pulsing laser, a driving force that set the initial rhythm. The magic happened when they observed the system's response. In any normal material, the atoms would respond at the same frequency as the driving laser. But in these time crystals, the atoms responded at a different, slower frequency. Even when the laser pulses were made slightly imperfect, the time crystal maintained its own rigid, stable rhythm, locked into its own preferred period of oscillation. It was a new phase of matter, one that was intrinsically out of equilibrium, yet astonishingly stable, resisting the universal pull toward disorder. The potential implications of this discovery ripple outward, touching some of the most fundamental concepts in science. For our understanding of time itself, time crystals present a profound puzzle. They are systems that have a preferred clock, a built-in tick-tock that defines their existence, challenging the notion of time as a featureless, flowing river. In the realm of quantum computing, they offer a beacon of hope. One of the biggest obstacles in building a practical quantum computer is decoherence, the tendency for fragile quantum states to be destroyed by tiny vibrations or temperature fluctuations from their environment. The remarkable stability of time crystals, their ability to maintain a coherent quantum state while being periodically driven, suggests they could be used to protect quantum information. They could act as perfect, naturally error-resistant quantum memory, a foundational component that could one day make robust quantum computers a reality. This is matter that isn't just sitting there, it's matter that is actively, perpetually keeping time, and in doing so, it might just hold the key to unlocking the next generation of technology. The mesmerizing, repeating dance of atoms in a time crystal is more than a scientific curiosity. It is a glimpse into a deeper layer of physical law, where the very fabric of reality may have a rhythm all its own. We've looked at dark energy as a constant force, a gentle but relentless pressure inherent to the vacuum of space. But what if dark energy isn't gentle at all? What if it's something far more ferocious, a force that doesn't just accelerate the universe's expansion, but intensifies over time, growing stronger and more destructive as space itself stretches? This terrifying possibility is known as phantom energy, and it leads to a cosmic doomsday scenario so absolute it makes the heat death seem almost peaceful by comparison, the Big Rip. To understand phantom energy, we need to introduce a specific number that cosmologists use to describe the nature of dark energy, called the equation of state parameter, denoted by the letter W. Think of W as a cosmic ID card that tells us how a particular form of energy behaves as the universe expands. For the simple cosmological constant that Einstein envisioned, this value is exactly -1. This constant energy density produces a steady, repulsive gravity that drives acceleration. But what if W is less than -1? What if it's, say, -1.5? This is the realm of phantom energy. A value less than -1 implies something truly bizarre. The energy density of this phantom field doesn't stay constant as the universe grows. It actually increases. As space expands, this mysterious energy doesn't dilute. It becomes more concentrated, more powerful. It's as if you were blowing up a balloon, and the bigger it got, the higher the air pressure inside became, forcing it to inflate faster and faster in a runaway feedback loop of self-destruction. The consequences of this ever-strengthening repulsive force are almost too violent to comprehend. It means the acceleration of the universe isn't just a constant, it's exponential. The rate of expansion doesn't just increase, the rate at which the rate increases itself accelerates. In such a universe, the repulsive gravity of phantom energy would eventually become so overwhelming that it would not just push galaxies apart. It would overcome every single force that holds the cosmos together, from the weakest gravitational bonds to the strongest nuclear forces, systematically dismantling the universe from the largest scales down to the very fabric of reality itself. Let's walk through the hypothetical timeline of this cosmic cataclysm. Imagine we're in a universe dominated by phantom energy about 60 million years before the end. The first structures to go would be the great cosmic filaments and walls of galaxies, the largest gravitationally bound structures in the universe. The phantom energy's repulsion would now exceed the gravitational pull that holds these vast superclusters together. They would simply be torn asunder, their constituent galaxy clusters flung apart at speeds exceeding the speed of light relative to each other, vanishing from one another's view forever as the space between them expands too quickly for light to ever cross again. As we move closer to the end, the destruction turns more personal. Roughly 3 months before the final moment, the phantom energy's grip would tighten on our own local group of galaxies. The Milky Way and Andromeda, which are on a collision course in our current universe, would instead be violently ripped apart, their stars scattered into the accelerating void. Then, with just minutes to go, the horror comes home. the phantom energy's repulsive force would now surpass the Sun's gravitational hold on our solar system. Earth would be torn from its orbit, hurled into the blackness of intergalactic space, but there is no time to drift. Moments later, the same force would overcome the Earth's own gravity. Our planet itself would explode, its pieces flying apart as the phantom energy now exceeds the gravitational binding energy that holds the planet together. The final act is the most profound. In the last fleeting instance, less than a second before the end, the phantom energy's power would surpass the electromagnetic force, the very glue that holds atoms and molecules together. Every molecule in what was once your body, every piece of your desk, every mountain and ocean would be instantly torn apart, but the destruction doesn't stop there. In the final attoscon, the phantom energy would grow so strong that it would overwhelm the strong nuclear force that binds protons and neutrons together in the nucleus of an atom. Atomic nuclei would be shredded. Protons, neutrons, and electrons would be ripped away from each other, their components scattered. Ultimately, the very fabric of space-time itself would be torn asunder. The universe would cease to be a coherent, continuous fabric. It would become a foam of disconnected, causally disconnected points, a total and irreversible end to all structure, all information, and all possibility. The Big Rip is the most definitive end imaginable. It's not a quiet fading into cold and darkness. It's a violent, explosive disintegration of reality itself. While the evidence currently favors a cosmological constant with a steady equation of state, the phantom energy hypothesis remains a valid, if terrifying, possibility within our models. It serves as a stark reminder of just how little we understand about the dark energy that dominates our cosmos, and how the ultimate fate of everything we know hinges on the precise value of a single, mysterious number in the equations of cosmology. But let's rewind from the edge of total cosmic disintegration and return to the very beginning, to a theory that offers a completely different origin story for our universe, one that replaces a solitary explosion with a spectacular collision. We've already touched on the ekpyrotic universe model as part of a grander cycle, but it deserves a deeper look for its sheer audacity in reimagining the Big Bang. This model, developed by physicists Paul Steinhardt, Neil Turok, and others, directly challenges the dominant inflationary paradigm by proposing that our universe was born not from a singular point of infinite density, but from the violent meeting of two majestic parallel worlds. To truly grasp this, we need to fully immerse ourselves in the brain world picture. Imagine our entire cosmos, every galaxy, every star, every one of us as a three-dimensional membrane, a three-brain, existing within a higher dimensional realm known as the bulk. This isn't just a flat sheet, it's a vast, dynamic, three-dimensional surface, and we are fundamentally trapped within it, unable to perceive or move into the extra dimensions that surround us. Now picture another such universe, another three-brain, floating silently in this same bulk, parallel to our own but separated by a tiny gap. These two cosmic membranes are not static. They are drawn together by a force, perhaps something akin to a spring, across the hidden dimensions. Over trillions of years, they oscillate, moving slowly toward and away from each other in an endless, graceful dance. The stage is set for a truly epic event. When these two brains finally collide, the energy released is beyond all comprehension. It's not an explosion in space, but an explosion of space itself. The kinetic energy of the impact is instantly converted into a raging fireball of fundamental particles and intense radiation, flooding our entire brain and igniting the hot, dense state that we have come to call the Big Bang. In this breathtaking vision, the beginning of everything was not a mysterious singularity, but a well-defined physical event, a cosmic car crash of unimaginable proportions. One of the model's most compelling features is its ability to tackle the same cosmic puzzles that inflation was designed to solve, but through a completely different mechanism. Remember the horizon problem, the perplexing uniformity of the cosmic microwave background. Inflation solved this by taking a tiny, uniform patch and stretching it to become our entire observable universe. The ekpyrotic model achieves the same end result through a different means, the slow, gentle approach of the two brains before the collision. As the brains move closer together over an immense period, any irregularities, any wrinkles or variations in energy have time to smooth themselves out. The brains become increasingly flat and uniform, like two perfectly planed sheets of wood. When they finally collide, this pre-existing smoothness is imprinted onto the newborn universe, explaining why the temperature of the Big Bang's afterglow is so incredibly even across the sky. It's a solution born not of frantic stretching, but of patient, drawn-out preparation. Similarly, the flatness problem finds its resolution here. The relentless pull drawing the brains together acts to flatten their geometry over the eons leading up to the collision. Any initial curvature is gradually ironed out during this long, slow approach. By the time the brains meet, they are exceedingly flat, and this flatness is naturally transferred to the spatial geometry of our newly born universe. There's no need for a fantastically fine-tuned initial condition. The flatness emerges dynamically from the cyclical process itself. This model also provides a compelling origin for the seeds of cosmic structure. The quantum fluctuations that were present on the brains themselves get stretched and amplified during the collision, creating the tiny density variations that would later gravitationally collapse into galaxies and clusters of galaxies. The entire cosmic web, in this view, is the direct descendant of quantum jitters imprinted during a cosmic impact. Where the ekpyrotic model truly diverges from inflation is in its predictions for primordial gravitational waves. Inflation, occurring at an enormously high energy scale, should have generated a strong background of these space-time ripples, leaving a distinct swirling pattern in the cosmic microwave background. The ekpyrotic scenario, however, is a much lower energy event. The collision and the subsequent heating are far more gentle in comparison, and as a result, the model predicts an undetectably small signal of these primordial gravitational waves. This creates a clear, testable distinction between the two theories. If future experiments like next-generation cosmic microwave background observatories fail to detect the telltale signs of these inflationary gravitational waves, it would be a major point in favor of the ekpyrotic picture. This collision-based origin story presents a universe that is part of a much larger, hidden reality, where the most monumental event in our history was simply the latest encounter in an infinite, cyclic ballet of creation. We just explored the staggering idea that our own consciousness might be rooted in quantum processes within the brain, but this leads us directly to one of the most persistent and puzzling questions in all of quantum mechanics. Why does a single, objective reality ever emerge from the quantum fog at all? This is the quantum measurement problem in its purest form. At the tiny quantum scale, particles exist in a haze of possibility, a superposition of many states at once. Yet when we, or any measuring device, look at them, that haze instantly clears and we find one definite outcome. The moon is definitely in one place in the sky. The chair you're sitting on is solidly there. We all agree on a shared, objective world. But how does this consensus happen? What or who chooses which possible reality becomes the one we all experience? This brings us to a fascinating and powerful theory called quantum Darwinism, which proposes that the emergence of our objective reality isn't magic, nor does it require a conscious observer. It is the result of a natural selection process playing out in the quantum world. To understand this, let's revisit our long-suffering friend, Schrödinger's cat. In the famous thought experiment, the cat is in a superposition of being both alive and dead until someone opens the box and looks inside. The act of observation seems to cause the wave function to collapse into one state or the other. Quantum Darwinism completely reframes this situation. It says the key player isn't the person opening the box, it's the environment. The moment the radioactive atom interacts with the Geiger counter, the result of that interaction, whether the atom decayed or not, immediately begins to be broadcast out into the surroundings. Photons of light, air molecules, and even background radiation bouncing around inside the box will scatter off the Geiger counter and the cat itself. If the cat is alive, photons will bounce off its fur in a specific pattern. If it's dead, they will scatter off its still form differently. These scattered photons and molecules carry information about the state of the system out into the world. They become multiple, redundant copies of the same piece of data. This is where the Darwinism part comes in. Not all quantum states are created equal when it comes to survival in the environment. Some states are fragile and get disrupted immediately, wiped out by interactions with their surroundings. These are the superpositions, but other states are incredibly robust. They can interact with the environment and be copied over and over again without being destroyed. These robust states are called pointer states, and they are the quantum equivalent of a species that is perfectly adapted to its niche. In the case of the cat, the alive state and the dead state are both pointer states. Each one, once established, creates a specific, stable signature that the environment can faithfully replicate. A single photon scattering off the live cat carries a tiny bit of information. Billions of photons carrying the same information create a durable, objective record. The superposition state, where the cat is both alive and dead, is not a pointer state. It is incredibly delicate. The moment it tries to interact with even a single air molecule, it decoheres, it collapses into one of the two stable, copy-able states. The superposition is selected against, while the definite states are selected for, surviving and proliferating through the environment. Think of it this way. Imagine a single, beautifully carved statue in the middle of a vast, empty plaza. Now, imagine 100 different photographers with cameras all taking pictures of that statue from every possible angle. Each photograph is a copy of the same objective fact. The statue exists in that specific form. You don't need to see the statue itself to know what it looks like. You can just ask any of the photographers to show you their picture, and they will all show you essentially the same thing. The statue is the quantum system, the cat, or a particle. The photographers are the photons and molecules of the environment. The act of taking the picture is the process of copying information. The reason we all agree on an objective reality is not because some privileged observer looked at the statue first, but because the environment has taken trillions upon trillions of these photographs, creating a consensus so overwhelming that it becomes the only accessible reality for any other observer. When you, as a person, come along and open the box to check on the cat, you are not causing the collapse. You are simply tapping into this pre-existing, widely distributed environmental record. You are just another camera reading out the information that has already been redundantly encoded all around you. This process, known as decoherence, is the mechanism that explains the appearance of wave function collapse without needing to invoke any mysterious conscious observation. The transition from the quantum world to the classical world we perceive is not a sudden, mysterious event. It is a continuous, relentless process of information being copied into the environment, which selectively destroys fragile superpositions and amplifies stable, classical states. The pointer states that survive this process are the ones that are fit enough to leave multiple copies of themselves in the environment. This is quantum Darwinism in action. It provides a compelling, physics-based explanation for why the world at our human scale appears so definite and stable. The chair is solid because its molecular structure is constantly being measured and recorded by the air molecules and light photons bouncing off it, creating an objective consensus that you are now a part of. The theory doesn't necessarily solve every philosophical nuance of the measurement problem, but it gives us a powerful and elegant framework for understanding how our shared classical reality naturally emerges from the bizarre and counterintuitive quantum foundation beneath it all. And so we arrive at a theory that tackles one of the most tantalizing and troublesome ideas in all of science fiction and theoretical physics, the possibility of time travel. The concept is thrilling: the ability to journey into the past to witness historical events or into the future to see what awaits, but it comes with a host of logical nightmares. What if you went back in time and accidentally prevented your own birth? This is the classic grandfather paradox, and it's a seemingly insurmountable logical barrier. If you kill your own grandfather before he meets your grandmother, you would never be born, which means you could never have gone back in time to kill him in the first place. It's a perfect, mind-twisting loop of contradiction that suggests time travel must be impossible. But what if the universe itself has a built-in mechanism to prevent such logical absurdities? This is precisely the solution offered by the Novikov self-consistency principle, proposed by Russian physicist Igor Novikov. This principle makes a simple but profound assertion. If time travel is possible, then any actions taken by a time traveler were always a part of the timeline. You cannot change the past because you have already done whatever it is you are going to do. The past is not a fragile script waiting to be rewritten. It is a finished book, and your journey into a previous chapter was always written into the plot. To see how this works, let's put the grandfather paradox under the Novikov lens. Imagine you build a time machine with the express purpose of preventing a terrible event in your family's history. You travel back to the 1920s, intent on stopping your grandfather from meeting your grandmother. According to Novikov's principle, you will fail. Not because you're clumsy or lack resolve, but because the universe itself will conspire through an infinite series of tiny coincidences and improbable events to ensure the timeline remains consistent. You might take aim with your futuristic weapon, only for a sudden gust of wind to throw off your shot at the last second. Or you might arrive in the past, track down your grandfather, and just as you are about to confront him, you slip on a conveniently placed banana peel and knock yourself unconscious. Perhaps you successfully prevent the initial meeting, only to later discover that your intervention inadvertently caused a different meeting between your grandparents under circumstances you never knew about, one that still leads directly to your father's conception and eventually to you. In every conceivable scenario, your actions do not change the past. They were always the very events that shaped the past you remember. Your attempt to change history was, in fact, the mechanism that ensured history unfolded exactly as it did. The universe, in this view, is like a master storyteller who has already accounted for every possible twist, ensuring the narrative remains free of contradictions. This idea has profound and somewhat unsettling implications for two of our most cherished concepts, cause and effect and free will. Our entire understanding of reality is built on causality, the principle that a cause must always come before its effect. You throw a ball and then it breaks a window. Time travel seems to turn this on its head, allowing an effect, your existence, to reach back and eliminate its own cause. The Novikov principle restores order by essentially erasing the distinction. In a self-consistent timeline, your journey to the past is both the cause and the effect, a closed loop where everything is interconnected. The effect is baked into the cause from the very beginning. This leads directly to the question of free will. If you are destined to travel back in time and fail in your mission, did you ever truly have a choice? The Novikov principle suggests a deeply deterministic universe, one where our perception of free will is an illusion. Every decision you make, including the decision to become a time traveler, was predetermined and is an immutable part of the cosmic record. You are not the author of your life story. You are an actor following a script that was completed the moment the universe began, a script that includes your future journey into the past. Your feeling of making choices is real to you, but the outcome of those choices was fixed forever. While the Novikov principle offers an elegant solution to the problem of paradoxes, it is not the only game in town. It stands in stark contrast to the more popular idea of the multiverse, where every decision creates a branching timeline. In that model, if you travel back and kill your grandfather, you don't erase yourself. You simply branch off into a new, parallel universe where you were never born, while the original you continues to exist in the timeline you left behind. The Novikov principle rejects this proliferation of realities in favor of a single, immutable timeline where everything is perfectly consistent. It's a vision of the cosmos as a perfectly self-correcting system, immune to the meddling of time travelers, a universe that has already accounted for every single one of its own future manipulations. This isn't just a wild speculation. It finds some support in the solutions of general relativity, like closed time-like curves, which are paths through warped space-time that could, in theory, allow for travel into the past. The mathematics of these solutions often inherently require self-consistency, preventing paradoxes from ever arising. So while we may never build a working time machine, the Novikov self-consistency principle provides a breathtakingly elegant and logically sound answer to one of time travel's greatest riddles, painting a picture of a cosmos that is not a chaotic playground, but a perfectly orchestrated and unchangeable work of art. We have ventured from the quantum to the cosmic, from the birth of universes to the nature of consciousness. But now we circle back to one of our earliest and most radical ideas, ready to see it with new eyes and a deeper understanding. We return to the holographic principle, but this time we trace its astonishing origin story, a story that begins not with philosophy, but with the thermodynamics of the most destructive objects in the cosmos, black holes. It was here that physicists first stumbled upon the bewildering clue that reality might be a projection, and it all started with a question about chaos and order, about entropy. Entropy is essentially a measure of disorder, a count of the number of ways the microscopic components of a system can be arranged while still looking the same on a large scale. A neat stack of papers has low entropy. That same stack scattered across a room by a gust of wind has high entropy. It's a measure of lost information. In the early 1970s, a young physicist named Jacob Bekenstein made a revolutionary connection. He realized that if you throw something with high entropy, like a hot, disordered gas, into a black hole, it vanishes behind the event horizon. To an outside observer, the entropy of the universe appears to have decreased, which would violate the second law of thermodynamics. But the laws of physics are not so easily broken. Bekenstein proposed a brilliant solution. The black hole itself must have entropy, and a tremendous amount of it. That entropy, he argued, must be proportional to the surface area of its event horizon. This was a conceptual earthquake. In every other system we know, entropy is proportional to volume. The larger the container, the more ways you can arrange the molecules inside it. But for a black hole, the ultimate container, the maximum amount of entropy it can possess is not related to the vast, mysterious volume within, but to the two-dimensional area of its boundary. The event horizon, it seemed, was acting like a cosmic hard drive. Stephen Hawking initially disliked this idea, but his own subsequent work on black hole radiation not only confirmed it, he put it on a firm mathematical footing. The Bekenstein-Hawking formula states that the entropy of a black hole is 1/4 of the area of its event horizon in Planck units. This is an unimaginably huge number. A single black hole the mass of our Sun would have an entropy billions of times greater than all the entropy contained in all the stars, planets, and gas in the observable universe. But the profound implication was this: entropy is fundamentally linked to information. A system with high entropy has many possible microscopic states. It holds a lot of hidden information. So, if a black hole's entropy is proportional to its surface area, then the maximum amount of information that can be stored within that black hole is also proportional to that area, not its volume. Imagine a massive three-dimensional library. the standard assumption would be that the number of books it can hold, its information capacity, depends on the volume of the building. But the black hole told us something utterly different. It said that the total information content of this cosmic library is actually determined by the area of its walls. Every single piece of information about everything that has ever fallen into the black hole, every star, every planet, every person, every memory, is not lost in the dark interior. It is perfectly and completely encoded on the two-dimensional surface of the event horizon, painted onto the boundary in microscopic bits, each one no larger than a Planck area. This revelation was so bizarre that it took another 2 decades for its full cosmic implications to be realized. In the 1990s, physicists Gerard T. Hooft and Leonard Susskind took this black hole result and ran with it, pushing the logic to its ultimate, breathtaking conclusion. They asked a simple, staggering question. If this is true for a black hole, the most extreme object governed by gravity, could it be a fundamental property of our universe? Could the entire cosmos, which we experience as a rich, three-dimensional reality, actually be a holographic projection from a two-dimensional surface at its boundary? This is the holographic principle in its full glory. In this view, our three spatial dimensions are not fundamental. They are emergent, like a three-dimensional hologram emerging from a two-dimensional film. The true, fundamental degrees of freedom, the ultimate code of reality, live on a distant, enclosing surface. We and everything we see are a translation of that data. Think of it like a modern, ultra-immersive video game. The breathtaking, three-dimensional world you explore is not fundamentally three-dimensional in the computer's memory. It is rendered in real time from a vast, complex set of two-dimensional code and algorithms stored on a hard drive. The universe, according to this principle, operates in a similar way. The solidity of your hand, the depth of space, the swirl of a galaxy, all of it is a magnificent, dynamic projection. To visualize this for a black hole, picture its spherical event horizon. Now imagine that surface being tiled with unimaginably tiny pixels, each one a Planck length on a side. These are the smallest possible units of area in the universe. Onto this pixelated canvas, information is encoded in the simplest form possible. Binary bits represented by the presence or absence of a microscopic 1 or 0. When an object falls into the black hole, it doesn't just vanish. Instead, its information is instantly scrambled and smeared across the entire event horizon, adding to the intricate pattern of bits already painted there. The three-dimensional object is transformed into a two-dimensional description on the boundary. The interior of the black hole, with all its apparent volume, is completely described by this shimmering, dynamic data layer. Susskind and T. Hooft's radical leap was to propose that our cosmological horizon, the ultimate boundary of our observable universe, might function in the same way. The 100 billion galaxies, the dark energy, the very space between them, all of it could be a holographic image generated from a flat, two-dimensional shell at the edge of everything we can see. This principle represents one of the most profound shifts in our understanding of reality. A true fusion of gravity and quantum mechanics that suggests the universe is not what it seems, but a spectacular illusion woven from information. But as we contemplate the very real possibility that we might be living inside a simulation, it's worth recognizing that this is not a new fear born of our digital age. It is, in fact, one of the oldest and most persistent puzzles in all of philosophy, a branch of thought known as skepticism. Centuries before computer code was even a concept, the great philosopher René Descartes was wrestling with the exact same problem in the 1600s. He embarked on a radical quest to find a single, undeniable foundation for knowledge. To do this, he decided to systematically doubt everything he could possibly doubt. He questioned the evidence of his senses, noting that dreams can feel perfectly real while we are in them. he questioned logic and mathematics, wondering if some malevolent force could be deceiving him even about simple sums. He eventually imagined the most powerful deceiver possible, an evil demon, an entity of supreme power and cunning devoted solely to tricking him. This demon could be feeding him a completely fabricated reality directly into his mind, creating the illusion of a physical body, a room, a world, all while he was, in truth, just a disembodied consciousness being perfectly and consistently fooled. Descartes' evil demon is the 17th century equivalent of a supercomputer running a hyper-realistic simulation. The core challenge is identical. If the deception is perfect, what tool do you possibly have to detect it? This philosophical thread was picked up and refined in the 20th century into the more technological-sounding brain-in-a-vat thought experiment. Imagine that a brilliant but mischievous neuroscientist has carefully removed your brain from your body, keeping it alive in a vat of nutrient-rich fluid. This brain is then connected to a sophisticated computer that feeds it perfectly coordinated electrical signals, simulating every possible experience. The computer generates the feeling of a warm breeze on your skin, the sight of a sunset, the sound of a loved one's voice, even the seemingly solid sensation of your own body. From the perspective of your conscious mind, life would continue exactly as it does now. You would have memories, emotions, and a complete sense of a lived past, all of which were just data streams written into your neural circuitry. You could even have the memory of reading about this very thought experiment and the feeling of certainty that you are not a brain in a vat, but you would be wrong. This modern retelling strips away the supernatural demon and replaces it with a technological one, but the philosophical punch is the same. It forces us to confront the unsettling fact that our entire reality is mediated through our senses and our brain. We have no direct access to the outside world, only to the electrical interpretations our brain constructs. If those interpretations can be perfectly simulated, then we are forever trapped within them, with no surefire way to look behind the curtain. What makes the modern simulation hypothesis so much more compelling than these classical thought experiments is that it now has a potential partner in the hard, mathematical laws of physics. The universe, as described by our most advanced theories, behaves in ways that are strangely reminiscent of a constructed reality. Take the concept of quantized spacetime. In our everyday experience, space and time seem smooth and continuous. You can zoom in on a ruler forever, in theory, dividing the distance infinitely. But physics suggests this isn't true. There appears to be a fundamental, smallest possible unit of distance, the Planck length, and a smallest possible unit of time, the Planck time. You cannot measure anything smaller. Why would a fundamentally continuous reality have a resolution limit? In a simulation, however, this makes perfect sense. Any digital construct has a finite resolution. It is pixelated. The Planck scale could be the pixel size of our universe, the fundamental limit of the cosmic computer's rendering engine. Similarly, the speed of light could be interpreted as the maximum processing speed of the simulation, the rate limit at which information can be updated from one point in the computational grid to another. Nothing can happen faster than light because the processor cannot update causality faster than that set rate. Even the bizarre, counterintuitive rules of quantum mechanics start to look less like arbitrary laws of nature and more like clever programming optimizations. The famous uncertainty principle, which says you cannot know both the exact position and momentum of a particle, could be a data compression technique. Why render a particle with infinite precision when no one is looking at it? The probabilistic nature of quantum events where particles don't have definite properties until they are measured could be an example of lazy evaluation, a common programming practice where you only calculate the precise details of a system when it becomes necessary, saving vast amounts of computational resources. The universe doesn't need to fully render the spin of every electron in a distant star until that information is required by an interaction. The mathematical elegance of the universe, the fact that it can be described so perfectly by equations, also fits this picture. A simulated reality would, at its core, be a mathematical structure. Its laws wouldn't be approximations, they would be the actual source code. The fact that we keep discovering deeper and more beautiful mathematical principles governing the cosmos could be seen as us slowly reverse engineering the program we are running on. These aren't proofs, of course, but they are eerie consonances that give the simulation argument a scientific weight that Descartes' evil demon never possessed. So we are left with the ultimate, deeply personal challenge. Look around you, feel the solidity of the floor beneath your feet, the warmth of your own hand. Listen to the ambient sounds in the room. All of it feels undeniably real. But based on everything we've just explored, can you think of a single, foolproof test to prove that it is real? Any experiment you devise, any evidence you gather, would be processed by your senses and your brain, the very instruments that could themselves be part of the simulation. If you found a supposed glitch in the matrix, a strange coincidence or a visual artifact that defied explanation, how could you ever be certain it wasn't just a deliberately placed Easter egg or a random computational error that the system quickly corrected? The more you try to prove the reality of your world, the more you are forced to rely on the tools and logic of that same world, tools that would be just as simulated as the world itself. This is the prison of perfect skepticism. It is a loop from which there is no obvious escape, a hall of mirrors where every reflection only confirms the existence of the mirrors, but never what lies behind them. The true power of this idea is not in providing an answer, but in framing the question in a way that fundamentally destabilizes our confidence in the very ground of our being, forcing us to accept that the most real thing we experience, our own consciousness, might be the only real thing in a cosmos of magnificent, convincing illusion. And so we arrive at the single greatest unfinished chapter in modern physics, a quest that has consumed the brightest minds for nearly a century. This is the search for a theory of quantum gravity, the monumental effort to perform the ultimate scientific unification, marrying Einstein's theory of general relativity, which governs the immense cosmic dance of planets and galaxies, with the bizarre probabilistic rules of quantum mechanics, which dictates the frenetic behavior of the subatomic world. These two pillars of physics are each spectacularly successful in their own domains, but they speak completely different languages and are fundamentally, mathematically incompatible. When forced to meet, their equations explode into nonsensical infinities, revealing a deep crack in the foundation of our understanding of reality. The dream is to heal this rift with a single, coherent framework, a so-called theory of everything that would describe all known forces and particles under one elegant, overarching set of principles. To understand why this is so difficult, we need to look at why gravity is the ultimate rebel, the lone holdout in the quantum family portrait. The other three fundamental forces, the electromagnetic force, the strong nuclear force, and the weak nuclear force, have all been successfully described by quantum field theories. In these models, forces are transmitted by tiny, discrete packets of energy called gauge bosons. For electromagnetism, it's the photon. For the strong force, it's the gluon. These particles dance in and out of existence in the quantum fields that permeate space, and their interactions are beautifully calculable. Gravity, as described by Einstein, is different. It isn't a force pulling through space, it is the geometry of space-time itself. Massive objects like stars and planets warp the four-dimensional fabric of the cosmos, and this curvature is what we feel as gravity. The problem arises when you try to chop this smooth, continuous geometric fabric into tiny, quantized packets. Theorists have a hypothetical particle for gravity, the graviton, but when you try to calculate how gravitons would interact with each other using standard quantum field theory techniques, the math produces infinite, irremovable results. The calculations blow up, becoming meaningless. This is because gravity is so incredibly weak, a magnet can lift a paperclip against the entire gravitational pull of the Earth, that its quantum effects only become significant at the tiniest of scales, the Planck length, a distance so small it is to a proton what a proton is to a person. At that scale, the very notion of a smooth, continuous space-time, which both general relativity and quantum field theory depend on, is believed to break down. We are trying to merge two theories that are built on mutually exclusive assumptions about the nature of reality itself. For decades, the most famous contender in this grand quest has been string theory, which we explored earlier with its vision of vibrating strings and hidden extra dimensions. But it is not the only game in town. A powerful and compelling alternative has been steadily developing, one that takes a radically different approach. This is loop quantum gravity, or LQG. While string theory attempts to unify all forces by positing that everything is made of strings, loop quantum gravity is more direct and conservative in its ambitions. It doesn't try to be a theory of everything in one go. Its primary goal is to quantize gravity itself, to describe the fabric of space and time using the well-established principles of quantum mechanics. Its foundational insight is breathtaking. Space itself is not smooth and continuous. It is not a featureless backdrop against which the drama of the universe plays out. Instead, at the tiniest possible scale, space is granular. It is composed of finite, indivisible quanta, much like a piece of fabric, which appears smooth from a distance but is revealed under a microscope to be woven from individual threads. In loop quantum gravity, these fundamental threads of space are visualized as tiny, one-dimensional loops. Imagine an impossibly fine mesh, a network of interconnected rings, with each ring representing a single quantum of area. These loops themselves are not in space, they are space. They are the fundamental building blocks of geometry. Where several loops intersect, you get a node representing a discrete quantum of volume. This entire dynamic network is called a spin network, and it evolves over time, creating a structure known as a spin foam. Picture a bubbling, effervescent foam where each bubble is a tiny quantum of space-time, constantly changing and reconnecting. This is the hidden texture of our cosmos, a seething, granular geometry at the Planck scale. The smooth, continuous space-time of general relativity is an illusion that emerges from this frenetic, underlying quantum activity, much like the smooth surface of a pond emerges from the chaotic motion of trillions of water molecules. This radical reimagining of space leads to profound physical consequences. One of the most stunning is the resolution of the Big Bang singularity. In standard cosmology, the Big Bang is a point of infinite density and temperature where the laws of physics break down. In loop quantum gravity, because there is a smallest possible unit of volume, you cannot compress matter and energy into an infinitely small point. Instead, the mathematics of LQG suggests that the collapse of a previous universe could have reached a maximum density and then bounced, rebounding into the expanding universe we see today. This gives us a compelling model for a big bounce, a cyclical universe without a true beginning or end, completely avoiding the troublesome singularity. Similarly, at the heart of a black hole, another fearsome singularity is replaced by a region of extremely high but finite density. The theory provides a natural cutoff, a point where quantum geometry prevents the complete breakdown of physics, offering a potential pathway to understanding what truly happens in these most extreme environments. The journey to quantum gravity is far from over, with both string theory and loop quantum gravity presenting formidable mathematical challenges and, as yet, no experimental proof. But the very existence of these profound and competing visions shows the incredible fertility of human thought, as we strive to weave the two great tapestries of modern physics into a single, coherent picture of a cosmos built from a spinning, granular foam of space-time itself. If you thought phantom energy and the Big Rip were the most dramatic ways the cosmos could end, prepare for a finale that is both more subtle and more absolute. This is the vacuum metastability event, a hypothesis that strikes at the very heart of cosmic stability, suggesting that the empty space we take for granted is not the true, enduring foundation of reality, but a precarious ledge over an abyss. To grasp this, imagine the universe's vacuum not as a state of pure nothingness, but as a field of energy, a kind of underlying hum that defines the laws of physics we experience. According to our best models, this vacuum state has a specific energy level, much like a ball sitting in a valley. For our universe to be truly stable for all time, this ball should be resting at the very bottom of the deepest possible valley, what physicists call the true vacuum. This would be a state of ultimate equilibrium where the laws of physics are fixed and unchanging forever. The terrifying possibility raised by the vacuum metastability event is that our vacuum is not in this true lowest state. Instead, our ball might be sitting in a small, local dip on the side of a much, much deeper valley, a false vacuum. It's a state that appears stable for now and has been stable for billions of years, but is fundamentally precarious. It's a cosmic accident waiting to happen. The mechanism for this catastrophe is one of the strangest in all of quantum physics, quantum tunneling. In the classical world, a ball doesn't have the energy to roll up and out of its local dip, it's trapped. But in the quantum world, particles and fields don't play by these strict rules. There's always a tiny, non-zero probability that they can simply tunnel through an energy barrier they classically shouldn't be able to cross. It's like the ball in our local valley suddenly, spontaneously, appearing on the other side of the hill without ever having rolled over the top. On the scale of the universe's vacuum, this quantum fluctuation could happen anywhere at any time. A tiny, microscopic bubble of true vacuum could spontaneously nucleate, a region where the Higgs field, which gives particles their mass, has shifted to its true, lowest energy state. In this new region, the fundamental constants and the very laws of physics would be completely different from our own. The strength of gravity, the nature of electromagnetism, the stability of atoms, all of it would be rewritten according to a new, alien set of rules. Once this bubble of true vacuum appears, the real horror begins. The energy difference between our false vacuum and the true vacuum is colossal. This creates an immense negative pressure at the bubble's boundary, causing it to expand outward at the speed of light. Not through space, but by rewriting space itself as it goes. The boundary of this bubble is a wall of incalculable energy, a wave of new physics sweeping across the cosmos. As it expands, it doesn't push matter aside like a shock wave. It fundamentally transforms everything it touches. Imagine looking up at the sky and seeing a perfectly dark sphere appear, growing larger by the instant. As its edge passes through a star, the star doesn't explode. It simply ceases to be a star. The very rules that allow nuclear fusion to happen, that hold protons and neutrons together, are instantly invalidated. The star and any planets orbiting it are dismantled into their constituent particles, which then themselves dissolve as the new laws of physics take hold. There is no destruction in the conventional sense, only an absolute and instantaneous erasure of the reality we know, replaced by something entirely other. The bubble would continue to grow at light speed, leaving behind a universe that is, for all intents and purposes, dead to us, its previous history and structure rendered irrelevant by the new, dominant physics of the true vacuum. The sheer scale of this threat is matched only by its incredible improbability. Based on our current measurements of the Higgs boson mass and other parameters, if our vacuum is indeed metastable, the expected time for such a quantum tunneling event to occur is staggeringly long. We are talking about timescales of 10 to the power of 100 years or more, a number so vast it dwarfs the current age of the universe, which is a mere 10 to the power of 10 years. To say the odds are astronomically low is a profound understatement. They are hypercosmic. you are statistically far more likely to spontaneously quantum tunnel through your chair and appear on the other side of the world than you are to witness a vacuum decay event in your lifetime. In fact, the universe will likely see its last star die out in 100 trillion years, and all black holes evaporate over countless eons, long before a vacuum decay event becomes remotely likely. So, while the physics is sound and the scenario is terrifying in its finality, it is not something to lose sleep over. It serves instead as a humbling reminder of the profound fragility of our cosmic order, and the fact that the laws we consider immutable might just be a temporary, local configuration in a much vaster and more strange landscape of physical possibility. And so we reach the 30th and final theory in our journey, a concept that brings us full circle, tying the very existence of the cosmos directly to the act of our own observation. This is John Archibald Wheeler's participatory anthropic principle, and it stands as perhaps the most profound and dizzying idea of them all. We've already explored the anthropic principle, the notion that the universe must be compatible with observers because we are here to see it. But Wheeler, one of the towering figures of 20th century physics, took this a dramatic step further. He proposed that observers are not just passive products of a pre-existing cosmos, we are active participants in its creation. In his own evocative words, he suggested that the universe only comes into being through the acts of observation, that it requires what he called observer participancy to achieve a definite reality. This isn't just a tweak to quantum mechanics, it's a complete reinvention of the relationship between life, consciousness, and the cosmos, proposing a stunningly circular model of existence. To grasp the sheer scale of this idea, we need to revisit the quantum measurement problem one last time. In the classic double-slit experiment, a particle behaves as a spread-out wave of possibilities until a measurement forces it to choose a specific location, collapsing its wave function into a single, concrete event. Wheeler took this quantum weirdness and projected it onto the grandest possible stage. He devised a thought experiment called the delayed choice experiment, which shows that a particle's decision to behave as a wave or a particle can be made after it has already traveled its path, based on a choice the experimenter makes in the present. This implies that our observations now can retroactively determine the past history of a quantum system. Wheeler then asked the ultimate delayed choice question: what if we apply this logic to the entire universe? We are all made of quantum particles. The light from distant galaxies, which has been traveling for billions of years, is also a quantum system. When we today finally point our telescopes at the cosmic microwave background, the oldest light in the universe, and make a measurement, we are collapsing the wave function of the entire cosmos. Our observation in the present is, in a very real sense, deciding the specific history of the universe all the way back to its origin. We are choosing a past that led to our own existence. This leads to Wheeler's most breathtaking vision, a self-excited universe. Imagine the cosmos not as a linear timeline with a beginning and an end, but as a magnificent self-referential loop. Picture the ancient symbol of the Ouroboros, the snake eating its own tail, but this one is woven from swirling galaxies with a single, conscious eye at its center. In this model, the universe began in a fuzzy, undefined quantum state, a superposition of all possible histories. It expanded and evolved over billions of years, eventually giving rise to stars, planets, and conscious life. These observers, by the very act of looking back and questioning their origins, began to make measurements. They observed the redshift of galaxies, they detected the cosmic microwave background, they probed the quantum realm. Each of these observations was an act of participation, a moment where a conscious mind reached out and forced a specific reality to crystallize from the quantum haze. This cascade of observations, stretching from the first curious human to our most powerful modern telescopes, collectively solidifies a single, consistent cosmic history, a history that inevitably leads back to a Big Bang that was perfectly tuned to produce us. The universe brings forth observers, and those observers, through their acts of observation, bring the universe into definite being. It is a closed loop of existence, a self-excited circuit where the cosmos awakens itself. Consider the profound implications of this for the fine-tuning of physical constants. Why is the universe so perfectly calibrated for life? The participatory anthropic principle offers a radical answer. It's because we are here to select it. In the beginning, there was not one universe, but a vast potentiality of all possible universes, each with different laws. The act of observation by countless conscious beings throughout cosmic history has selectively reinforced the one timeline, the one set of physical laws that makes such observation possible. We are not the lucky winners of a cosmic lottery. We are the architects collaboratively building the very universe that gave us birth by the simple, profound act of looking at it. This idea elegantly sidesteps the need for a multiverse or a divine creator. The universe is its own cause and its own effect, with conscious life as the essential participatory link that closes the circle. It is a vision of a cosmos that is not merely inhabited by conscious beings, but one that is fundamentally built from and for consciousness. A grand, ongoing dialogue between the universe and itself, a conversation that began with a quantum question and is answered every time we gaze with wonder at the stars. From the holographic projection of our reality to the participatory act of a universe observing itself, we have ventured across a breathtaking landscape of ideas, a 30-theory journey that reveals a cosmos of almost unimaginable depth and strangeness. What emerges from this grand tour is not a single, tidy answer, but a magnificent tapestry of possibilities, each thread challenging our most basic assumptions about existence. We have seen that solid matter may be an illusion projected from a distant surface, that our universe is likely just one bubble in an infinite, frothing multiverse, and that the very fabric of space and time may be woven from a granular quantum foam. We've confronted the eerie silence of the cosmos and the chilling possibility of a great filter, while also considering that life itself might be a cosmic traveler, seeding worlds across the galaxy. We've grappled with the nature of our own consciousness, questioning whether it is a classical computation or a quantum phenomenon, and even whether the world we perceive is a base reality or an elaborate simulation. Through it all, one common, powerful thread connects these wildly diverse theories: the relentless human drive to understand. This is more than just a quest for knowledge. It is a deeply personal search for context, a need to find our place within this vast and often hidden reality. Are we a statistical fluke in a cold, accidental universe, or are we an essential participant in the very act of cosmic creation? The theories we've explored offer every shade of answer in between, revealing that the universe is not only stranger than we imagine, but stranger than we can imagine. This journey fundamentally reshapes our perspective. It teaches us that mystery is not a sign of scientific failure, but an invitation to explore further. The puzzles of dark matter and dark energy, the paradoxes of black holes, the fine-tuning of physical constants, these are not dead ends. They are the frontiers where our next great discoveries await. They remind us that humility is the beginning of wisdom. For all our technological prowess, we have yet to determine what makes up 95% of the universe. We cannot reconcile our two most successful theories of physics, and we have no definitive proof of whether we are alone in the cosmos. This isn't discouraging, it's liberating. It means the greatest adventures of the mind are still ahead of us. The true value of exploring these 30 theories lies not in choosing a favorite, but in embracing the collective wonder they inspire. They expand our sense of what is possible, stretching the canvas of reality to include hidden dimensions, cyclical time, and a cosmos that might be fundamentally mathematical, conscious, or participatory at its core. They grant us the profound privilege of peering behind the curtain of everyday experience, catching glimpses of a reality so complex and beautiful that it fuels our curiosity for a lifetime. Now, this cosmic conversation continues with you. The search for understanding is not a solo endeavor confined to laboratories and lecture halls. It's a shared human experience. We want to hear which of these 30 theories completely reshaped your view of reality. Was it the holographic principle that convinced you we're living in a projection? Did the chilling logic of the Great Filter make you ponder the fate of civilizations? Or was it the participatory universe that gave you a new sense of connection to the cosmos? Let us know in the comments below. The most fascinating discussions often start right there. If you enjoyed this mind-bending journey through the universe's hidden layers, if it made you look up at the night sky with a fresh sense of awe, then do us a tremendous favor and give this video a like. It truly helps us continue creating deep dives into the mysteries of existence. And for more explorations that challenge what you think you know, from the secrets of quantum physics to the enigmas of distant galaxies, make sure to subscribe to the channel and hit the notification bell. The universe is full of wonders, and together we've only just begun to uncover them. Thank you for joining us on this incredible